So today we'll continue. We're kind of executing out of order, as you can see, covering topics a little bit out of order. These are topics that we wanted to cover, but they're getting reordered because of dynamic events like me being out of town, things like that. So hopefully you learned about GPUs last time. We're going to have another GPU lecture next week. Today we're going to finish memory interference and quality of service, and tomorrow hopefully we'll cover emerging memory technologies. But there is one announcement that I will make. Next week we have a special, very special lecture actually. This doesn't happen very often. On Friday you're going to learn about prefetching from someone who has really built a lot of prefetchers. Stefan Meyer from the platform architecture team at Apple. They do actually design a lot of prefetchers in that thing, and probably many with chips as well. He's going to talk about prefetching. This lecture will not be recorded. It's not going to be online anywhere. So you're not going to be able to access it if you don't come here. So if you're listening to me, you'd better come here next Friday, because this is going to be part of the topics that are part of the exam. Does that sound good? Okay. And you can feel free to ask questions. You're not guaranteed to receive answers, especially if you ask some certain questions, but this is a good opportunity for you to learn from someone who's been really building state-of-the-art prefetchers for a long time. Okay, now let's move to what we were discussing before. We were talking about quality of service. Do you remember this? Okay, basically our goal here was to really build quality of service aware memory systems, and there were basically three major questions that we were trying to answer. How do we reduce inter-thread interference? How do we control inter-thread interference? And how do we make the memory system more configurable and flexible? And we were looking at techniques that essentially try to do all of them at the same time, even though we didn't really focus on all parts of the different techniques. And just to jog your memory, we started essentially with memory scheduling. We discussed there were two different approaches to actually building quality of service aware systems. One is making the resources smart, meaning that incorporating quality of service mechanisms or answers to these three questions to each of the resources, shared resources that you have in the system. And these are three example shared resources. But you could of course extend these to SSDs, for example, right? You could imagine any shared resource is it can become smart, can incorporate quality of service techniques. In fact, internet routers, for example, incorporate a lot of quality of service techniques, and they're some of the most major shared resource across computers that we have today. But we're not going to talk about internet routers here. The other option is really having the resources dumb, meaning not incorporating a lot of or any quality of service technique to a single resource, but controlling interference in some other manner by injection, for example, into the shared resources. Actually, internet does both of them. If you look at networks, they have smart routers. They also have congestion control. When you inject requests into the internet, you're throttled if you're really causing trouble to someone else, for example, or if there's too much congestion on the internet. So that's an example of controlling interference in some other way than making the shared resources smarter. So you can already see that these are two different approaches, but they can be combined together. And that's true for other shared resources that we're examining here as well. Make sense? By the way, feel free to ask questions. We don't need to cover all of the slides here. I'm going to cover a bunch more memory schedulers right now. And remember, we had four different fundamental interference control techniques. We're going to try to finish all of them today, but we're going to focus a little bit more on memory scheduling, which hopefully you're having fun with during your lab. How many people have started the lab? I heard some discussions. Are you enjoying it? How many people are enjoying it? Okay, that's good. I see some hands. Some people are reluctantly raising their hands. You'll enjoy it more. Maybe we should have you build prefetchers after next week's lecture using Ramulator. Okay, but basically prioritization is something that you've been getting some hands-on experience with. What you're not getting hands-on experience with is all of these. Clearly you're not able to do labs for all of these, but these are also techniques that are employed and also fundamental interference control techniques. But let's continue this prioritization a little bit. I wanted to do a little bit deeper dive on this one because there's a lot of work in this area. There's comparatively less work in these three other areas. Okay, remember we discussed one approach to prioritization. This was total time fair memory scheduling. I'm not going to go through the details. Basically, you want to estimate the slowdowns and you want to balance the slowdowns, right? And we talked about the upsides and downsides. And this was mainly focused on fairness, but being fair can actually improve performance because it enables some unfairly treated cores to make fast progress now. Right? That's the upside. It's not, in particular, there are no mechanisms that are built into stall time fair memory scheduling that try to improve performance. It's really trying to improve this fairness by balancing the slowdowns. But being fair actually improves performance by increasing the utilization of the cores. That's very interesting. Sometimes being fair is not good for performance, but in some cases, being fair is good for performance. But this is not the case if you actually look at the paper. Sometimes being fair is actually bad for performance also, but that's not the common case. So the downside, it doesn't handle all types of interference. As we discussed, it's complex to implement, and slowdown estimations can be incorrect. If you think Atlas and Bliss are complex to implement, try implementing this, and you will see that this is much, much worse. Okay, and actually this is true as we discussed. If you have time, we'll talk about some other methods of estimating interference, estimating slowdowns that are much more accurate, but we'll see if we have time. Basically, I'll give you the high-level idea. What stall time fair memory scheduling does to estimate slowdown, estimate how much a thread is slowed down compared to when it's run alone, is it really does very low-level counting. Basically, it counts every request, and it tries to figure out how much each request is delayed, and tries to based on that delay, it tries to see how much an application gets delayed compared to when it's run alone. That's the idea, basically. So it does very low-level accounting. And it turns out that low-level accounting is very, very hard to get right. The future work that improved on this, it's called MICE, for example, Memory Interference Induced Slowdown Estimation, or ASM, Application Slowdown Model. What they do is they basically put the problem to a high level. They basically don't try to estimate what happens to every single request. They try to estimate what happens to the request service rate of an application. So you have a request service rate when you're running alone, when you have a request service rate when you're sharing resources with others, and your slowdown is essentially the division of those two. If your request service rate has gone down by 20x, for example, you're slowing down by 20x. That's the idea, assuming you're memory intensive. And it turns out that estimating the request service rate of an application at a high level is much easier than estimating the interference that's caused to every single request. Does that make sense? Because request service rate, if you think about request service rate, what does that mean? How many requests are serviced in a given time period? Right. If you have 10 requests serviced in a given time period t when you're running alone, and then if you have 5 requests serviced in the same given time period t when you're running together, your slowdown is like 2. Okay. Of course, there are details here, which we're not going to go into right now, but that's the difference between very low-level accounting for interference versus high-level accounting. It turns out this high-level accounting that raises the level to a higher level actually provides much better accuracy in terms of slowdown estimation. Yes?
Is this the same way that the QoS figures now just
which one? So this STFM is, yes, it's a very similar idea,
okay.
Yes, but not the request service rate idea. That's a completely different idea. But the goal in the end, the high-level goal is really slowdown estimation.
Yeah, like proportional.
Exactly. So yeah, the goal is the same, but the implementations are completely different. How we actually estimate the slowdowns are completely different. So this is an error of, for example, 40% in the slowdown estimations, whereas if you try to estimate based on the request service rates, it's about 10%. Okay, so let's see if we get there. Okay, and then we discussed parallelism-aware batch scheduling. If you remember, the idea was to batch requests and then ensure starvation freedom because of, due to this batching, and then have a ranking of different threads within a batch and serve the threads based on that ranking so that you can exploit bank parallelism. That's the basic idea. And this was actually the first scheduler to address bank parallelism destruction across multiple threads. So in that sense, it's really trying to improve performance, right? It's not just tackling fairness or starvation. It's really trying to improve performance by trying to ensure that requests that are sent in parallel to different banks are actually serviced in parallel by different banks. So it's really trying to reduce the stall time of applications. It's a simple mechanism, much simpler compared to SCFM. It's still more complicated than what you're implementing in your lab. And if you want to implement it, feel free. And batching actually provides fairness and starvation freedom. Batching is actually a very good mechanism for starvation freedom in general. And ranking enables parallelism awareness. Of course, this has downsides also. As I mentioned at the end of last lecture that I delivered, this doesn't prioritize the latency-sensitive applications. Basically, if an application is latency-sensitive, if it generates requests once in a while, and if there's some other application that's generating lots of requests, the other application essentially becomes a hog inside a batch, because the application that is requesting only once in a while needs to wait for the previous batch to finish. If that previous batch is reasonably large, then you have a problem. So this is something that we wanted to solve with the Atlas scheduler that you're actually implementing. I'm not going to go into the details of Atlas since you're implementing it, but hopefully you're having fun with it. I'll give you the basic high-level idea. This is actually one of the simplest schedulers that were implemented, although it still uses ranking, which is a source of complexity that Bliss eliminates, for example. So basically the summary is, the goal here is really to maximize system performance. We didn't really care about fairness here. Although in some cases this could improve fairness also, it depends on the workload. So basically the basic idea is to prioritize the thread that has attained the least service from the memory controllers. That's why it's called adaptive per thread least attained service scheduling. This actually is similar to some of the scheduling mechanisms that are employed in operating systems. People try to implement least attained service scheduling on operating systems. Which thread has attained the least service from the processor so far, and schedule that thread earliest so that it can make more progress. That's the idea. And this improves system throughput. How many of you have read the Atlas paper so far? Okay, that's good. Some people are going to read it, hopefully. That's good. Basically, this improves throughput, and it actually, under certain conditions, it actually maximizes throughput if you have a single server, because it's a form of shortest job first scheduling. And if your attained service correlates with the remaining service, then essentially you're predicting the length of the job by using attained service so far, the amount of service you attained so far as a predictor for the service that you need to give to a thread so that you can complete that job. Does that make sense? I think if you read the paper, this will become more clear. But essentially, it's a shortest job first scheduling mechanism where you think, where you quantify the shortness of a job with the service that the job has attained so far. I think of this as like there are examples. If you basically, if you have attained a lot of service so far, meaning that if you requested a lot of memory, you're going to request a lot more from the memory. I think of, from a human perspective, if you've slept a lot so far, you're going to sleep a lot more. But if you've slept little, it's likely that you're going to sleep little. It's actually the rule of these long-tail distributions, essentially. Pareto distribution, and you can see that the Pareto distribution is really what enables this. But I'm not going to go into details of this. But have fun reading the paper. I really like this paper from that perspective. Okay, so basically what does it do? It ranks threads based on the attained service in the past time interval, anticipating that the threads are going to behave similarly in the next time intervals. That's another assumption that we're making over here, right? If that's not true, it's not going to work clearly. And it enforces thread ranking in the memory scheduler during the current interval. And it ranks the threads that have attained service the least, the highest, meaning that they're prioritized over others. Meaning, again, assuming that they're shorter jobs, they're not going to request a lot of memory. Meaning that they're kind of light, they're not very memory intensive. So it improves system performance because these threads are more likely to keep their cores busy. Make sense? So are you seeing these results in your implementation? Not yet? Look at the workload. So these things are very much dependent on workloads in general. If the workloads are, for example, very homogeneous, you may not see a lot of benefits from here. You really need heterogeneity in your workload in this, although we provided you workloads, which hopefully give you some results. Okay, so that's the basic idea. So I'm not going to go into details. As I said, I'll give you the results. You've seen these results in the paper also. Basically, at the time this was designed, it provided the consistently higher system throughput than all previous scheduling algorithms because it was really designed to prioritize these light threads, if you will. But if you look at fairness, it's a different story, of course. Basically, it's not the fairest algorithm. Fairest algorithm was still PAR-BS. I'm going to show you some other results later on. But you can also, I like this graph because this looks at system throughput in a 24-core system with lots of with memory controllers varied. You can see that this is an extremely bandwidth constrained system. You have 24 cores and only one memory channel. Whereas here, this system has a lot of bandwidth, 24 cores and 16 memory channels. You would not build either system, I think. if you're a good designer, you would probably build somewhere here. And here you can see that the performance improvements are high. But if you're really bandwidth constrained, this Atlas scheduler actually gets you higher performance than any other scheduler. Although you would not build this system, I think. And if you don't have a bandwidth problem, then memory scheduling is not a big issue, as you can see over here. So here you have ample bandwidth, and different memory schedulers look similar to each other, even though Atlas still improves performance by a blip, as you can see over there. Make sense? So there's something fundamental in this graph, meaning that if you don't have a bandwidth problem, scheduling is not a problem. But of course, bandwidth is cost, and you don't want to be here. You want to be somewhere here. And as a result, scheduling is important. And scheduling becomes more and more important as you become more bandwidth constrained over here. Okay. This is another picture that I like from that paper, which you probably have seen. Basically, this is varying the number of cores, keeping the number of memory controllers constant. As you can see, as you increase the number of cores, you get better performance benefits compared to RBS. And as you reduce the number of cores, you get smaller performance benefits. Again, that's also expected because of the bandwidth pressure that you have on the system. Okay. Any questions? And you have a lot of freedom in implementing your scheduler, by the way. I think I've seen some discussions on Moodle with questions. These are good questions, keep them coming. But in the end, you will have a lot of freedom. But make sure that you explain what you've done. And you will find out that this is actually a real issue that everybody faces. Like if there's a paper that's written, and your task is to implement what the paper is doing. But there are cases where not everything is explained. That's true. There's actually no paper that I know of that explains everything that you can do. If they do, that will be a 100-page manual, not a paper. So basically, you will have some freedom in exploring and experimenting, and especially in Atlas. I think Bliss is a lot simpler to implement. In Atlas, you have some choices that you will make. Okay, so let's talk about the upsides. So basically, this was designed for throughput, so it's good at improving overall throughput. Hopefully, you will see that. Compute-intensive threads are prioritized. It's low complexity, much lower complexity than previous schedulers. And even though I didn't talk about this, but this, because it has a long interval size, this coordination among controllers happens infrequently over here. You read the paper. I'm not going to talk about this in detail. But whenever you actually want to make similar decisions across different controllers, you need to coordinate the controllers. And if you have multiple controllers, you have a coordination problem between controllers. I think this is very interesting, actually, from a theoretical perspective. In fact, we had written a distributed computing paper that appeared in PODC in the same year related to this, analyzed the problem from a complexity perspective. But this issue becomes more important if you have a vapor scale engine, for example, if you have lots of controllers, and if you need to coordinate between them. Okay, of course it has downsides also. Basically, one downside is really high unfairness. Lowest or medium ranked threads get delayed significantly. I think of these as, I will give you a better analogy when we talk about the next work, but you have these threads they're all very different from each other. Some of them are like elephants, huge elephants. Some of them are like mice. And if you have a scheduler like first ready, first come, first serve, elephants kill the mice, right? Because elephants are very heavy, and they basically are prioritized and they destroy the mice. Here, mice get prioritized over the elephants. Right? As a result, system throughput improves, but some of the elephants basically get delayed significantly, especially if you're an elephant that's not huge, but it's really medium-sized. Does that make sense? I like this analogy because if you're a huge elephant, you're very slow anyway. Nobody's going to touch you. You're going to run slowly. If you're prioritized, you're going to run still slowly. But if you're a medium-sized elephant, and if you're getting delayed behind a lot of medium-sized elephants, then you have a problem. Right? This will become more clear when we talk about the next work. Okay, I mean, you could argue that also ranking is complicated, and that's true actually. Okay, so let's talk about the next one. Any questions so far? I assume everybody will have a perfect implementation of Atlas. Okay, good. So let's talk about the next work. Basically, I think the takeaway here will be applications are heterogeneous, so you need to have policies that are also heterogeneous. All of these policies that we've discussed so far are homogeneous. They don't treat different applications differently. They essentially treat all applications similar. And like a lot of other things that we've discussed in this class, heterogeneity is a very fundamental principle because the world is heterogeneous, so your policies also need to be adapting to the heterogeneous world. Let's take a look at the motivation of this. Basically, in this work, we basically don't want to give up fairness or throughput. We want best of both worlds. And let's take a look at how scheduling algorithms that we've seen fare based on some workloads, based on some evaluation that's done over here. Ideally, you would like to be over here, right? You want to have higher system throughput and lower, higher fairness, of course. In this case, as you can see, we're changing the definition of fairness a little bit. We're calling it maximum slowdown. That was actually done in Atlas as well. Atlas evaluated multiple metrics. But basically, maximum divided by minimum slowdown is one definition of fairness. And when I talked about fairness for the first time, I said that this is a very hairy metric. Well, coming up with a metric that's good under all cases is very hairy. In this case, we said that maybe max divided by min is not the right metric, because who really cares about max divided by min? As long as you keep max slowdown as low as possible. Right? For example, the question, if you have a max slowdown of 5 versus 6, which system is more fair? I would say a system that gives you a max slowdown of 5 is more fair because it bounds the slowdown of all applications. But of course, you could also argue that max divided by min may be better for the system that has a max slowdown of 6. That is possible. There is a higher max slowdown, but max divided by min may be lower. But then that means that a lot of more applications are running slower. So I like this metric because it has a notion of bounding the slowdowns. Although it's a bit harder to argue these metrics. The fairness by itself is a fuzzy thing, right? You define what's fair first, and then you define a metric for it. And by changing the definition of fairness, you change the metric. Okay. There's a treatment of this actually in some other works, but I'm not going to go into it. Okay, so basically, assuming that you have this metric, you want to minimize it. So Atlas actually has a system throughput bias. This is where Atlas lands, average across 96 workloads selected by this work. And PowerBS has a fairness bias. Basically, none of them are Pareto optimal, as you can see, if you're trying to optimize both metrics, because there's no scheduler that's here. And if you look at STFM, it's definitely not good. You would not pick, assuming this is true for all workloads, you would not pick STFM under any condition, right? And assuming you have the choices for these schedulers. FR-FCFS is not good, and it turns out FCFS is not good also. And there's a later picture that I'm going to show you. You can vary the parameters of these, and they vary in different ways. Basically, no previous scheduling algorithm provides both the system throughput, both the high system fairness and high system throughput at the same time. And we want to actually get the best of both worlds. And whenever you have a picture like this, if you remember the tiered latency DRAM picture, we had a similar picture, right? You get good capacity, but higher latency with some mechanism. With some other mechanism, you get bad capacity, but lower latency. What do? You try to combine the best of both worlds, which means that you resort to some sort of heterogeneity. And the idea here is the same, basically. Throughput versus fairness, these are two metrics that we're trying to optimize. And to optimize for throughput, I think we know this very well by now, you really want to prioritize the less memory-intensive threads, because less memory-intensive threads actually can keep their cores busy if they're prioritized. So basically, you want to prioritize the mice. Because the elephants, if you prioritize the elephants are slow, and mice don't want to get delayed behind the elephants because they get killed, if that's the case. Okay, so this is good for throughput, but this is bad for starvation and unfairness, because these elephants and middle or large elephants, the large threads that send a lot of requests to memory, now become delayed. So this is not good for fairness. Whereas if you look at a fairness biased approach, this is one way of thinking about fairness over here. Maybe what you do is you enable threads to take turns when they access memory. At some point, thread A is prioritized. At another point, thread B is prioritized. At another point, thread C is prioritized. And you basically change the ranking of the threads once in a while. That's a more fairness biased approach. Makes sense, right? It's kind of round-robin scheduling. That's one definition of fairness. That's round-robin fairness. Of course, it doesn't talk about stall time and all of the detailed application-level metrics. maybe this is not a good metric for application level fairness, but this may be a good, this is an intuitive notion of fairness. Clearly this enables the thread C not to start because it will have its time where it will inject its request and they will get serviced. But unfortunately this is not good for thread A because it's not always prioritized. In fact, it'll get delayed until it gets its next service time, which may be a long while, right? Because some of these threads have a lot of requests and this thread will still get delayed behind them. So you get reduced throughput in this case. So essentially the realization is that single policy is for all threads is insufficient. And you could replace your fairness biased approach with your favorite fairness biased approach. You will see a similar thing happens over here. So the idea is to try to achieve the best of both worlds. And we're going to exploit these principles, but we're going to do it in a heterogeneous manner. Basically, we're going to classify threads into two groups. Some threads are memory non-intensive. And if you want to really improve throughput, you would like to prioritize these memory non-intensive threads. Because as we discussed, this is good for throughput. And actually, if these threads are not very, very intensive, they're not going to destroy the fairness of others. The fairness problems are actually going to come from threads that are not going to be classified as memory non-intensive. So for fairness, the realization is that unfairness is really caused by memory-intensive threads being prioritized over each other. So if you have very light threads, these threads are generating requests once in a while, not often enough, and they're not, even though they're being prioritized, they're not delaying others, as much at least. But if you actually start prioritizing this thread over this thread, even though they may be equal, they start delaying each other significantly because this has a significant footprint on the memory access tree. So basically the realization of this work is you really want to treat these threads carefully if you care about fairness. And the idea is to shuffle the thread ranking between these threads once in a while prioritizing these threads over these. But of course there's another realization. These threads are still different from each other. They have different vulnerabilities to interference, as we will discuss. It turns out you don't shuffle symmetrically, you shuffle asymmetrically. Meaning some threads get to be the top thread more often than others. Does that make sense? Because they're more vulnerable to interference. Any questions? Okay, we'll see that vulnerability in a little bit. So let me give you the algorithm. I think I've given you the basic algorithm in a sense, but let's go into a little bit more detail. Basically, the idea is to group threads into two clusters and treat the clusters differently. These are hardware contexts, hardware threads essentially. These are threads that are running in your cores and hardware context. You classify them, the hardware classifies them as memory non-intensive versus memory intensive, and it forms two clusters, non-intensive cluster and intensive cluster. It prioritizes the non-intensive cluster for throughput, and it employs different policies within each cluster. It turns out even within the non-intensive cluster, threads are slightly different from each other, so you basically prioritize the least intensive threads over more intensive threads for throughput again. But this doesn't impact performance a whole lot because these threads are not generating a lot of requests anyway in general. In the intensive cluster, the prioritization mechanism is basically shuffling the thread ranking once in a while. You basically create a thread ranking and you shuffle it such that different threads become the top threads once in a while. And that provides you fairness. And that provides you starvation freedom. Also, all threads make progress. Does that make sense? Okay, cool. So let's take a look at this a little bit more detail. I don't want to spend a lot of time in the details, but I'd like to get your ideas also later on. But basically, how do you do the clustering? This is actually a complex mechanism. It's not a simple mechanism. It's more complex than PAR-BS actually because it has a lot of components. Basically, how do you do the clustering is an issue. If you don't do the clustering right, you may prioritize memory-intensive threads over some other threads, right? Which may not be good for throughput. Which may be good for throughput, but may not be as good for throughput, but which may be bad for fairness. So this paper does the clustering by sorting threads in terms of misses per kilo instruction, and basically checking the total memory bandwidth usage of all threads, and basically saying the group of threads that use a fraction of the bandwidth are deemed as the memory non-intensive cluster. And I think alpha is 10%, for example, in this work. Basically, the group of threads that use 10% of the memory bandwidth that's used in the system is deemed as the non-intensive cluster. Makes sense, kind of, right? It's a smaller group that's not using a lot of bandwidth. although that may or may not be good because it's not really looking at the individual threads intensities in this case. So clearly you can make the clustering better. You can have more sophisticated clustering mechanisms, like use machine learning or K-means clustering, some sort of clustering, but we don't do that. It's not clear if those are really that beneficial. Okay, and then between clusters, as we discussed, you prioritize non-intensive threads because they can make greater progress, and this doesn't degrade fairness because they're light, assuming the clusters are formed nicely. But this may not be true, actually. This is actually one of the Achilles heels of this algorithm. How do you form the clusters? If you don't form the clusters nicely, your fairness actually degrades. So getting these thresholds are actually difficult in really implementing this sort of algorithm in hardware. And we've seen this many times. That's why these algorithms are relatively hard to implement. And that's the motivation for Bliss later on, as we will discuss. Okay, so let's take a look at non-intensive cluster. We've already discussed this basically. Prioritizing the threads according to MPKI, such that lowest MPKI threads are prioritized over others, increase system throughput. That's good. And the most difficult part is really this part. Well, most difficult part may be clustering, but once you've done the clustering, how do you actually prioritize between these elephants is a difficult part. And as I mentioned, you periodically shuffle the priority of the threads, such that this is what happens here. Clearly, you need to have a time interval to be able to do this, and I'll show you in a later picture maybe. And this increases fairness. But the question is treating all threads equally good enough? Meaning that, let's say in a longer time interval, you have 100 slots, and each thread gets an equal share of those 100 slots as the top thread. I'm the highest ranked thread for 100 divided by n of these slots, where n is the thread number of threads that you have in the system. Is that good enough? Meaning that, is that the best for fairness or the best for performance? And it turns out it's not, because this thread may not need all of those slots, right? Because it may not be very vulnerable to interference. Whereas another thread may be very vulnerable to interference, and that may need all of those slots. So basically, we want to treat equal turns. Doesn't mean that you have the same slowdown. This is the difference between kind of round-robin fairness versus slowdown fairness. So we really want to look at the properties of the thread in terms of memory access. So let's take a look at how this happens. We'll look at a case study of two intensive threads. These are two extreme threads. One is random access and one is streaming. Whenever you want to study memory access behavior, these are two cases where you really want to study. Extremely random access and extremely streaming. That gives you a lot of insight. And then actually you can vary the random access and streaming behavior using micro benchmarks, for example. That's a very good way of understanding the algorithms without being too much coupled to the workloads. You can construct actually memory access streams using random access and streaming. So the question is, which one slow down more easily? Let me ask you that question. Any guesses? I have two threads that are both highly memory intensive, let's say, and they have equal number of requests. One is completely random access, and the other is streaming from the same rollover. Which one is slowed down more easily when they run together? Who wants to go first? Now we have a scheduling problem. Okay, go ahead.
The streaming one.
The streaming one. Why?
Because it already has the potential to do good, which you can remove.
Okay, I like that thinking. Oh, yeah, what about yours?
I was just thinking around robot criticality, so if it's streaming, you're more likely to actually benefit from robot criticality.
Okay.
If random access comes in between, you'll have to reach out and go back.
Okay, I see.
We'll slow down your code.
Okay, I see. I see where both of you are coming from, but I'm thinking of a different scenario. Yes?
Actually, it depends on the scheduling algorithm.
Okay.
If I see if there is a priority list, then streaming will perform better than random access. But if that's not the case, then maybe random access might
Okay.
not be good.
Okay, maybe I didn't set up the question really well. I was thinking of two threads that have an equal number of requests, a lot of requests, let's say, and they basically are running together versus when they're running alone. which one slows down more easily if you prioritize one over the other. So you have two different cases. In experiment 1, you prioritize the random access thread, you look at slowdown. In experiment 2, you prioritize the streaming thread, and you look at slowdown. Which slowdown is higher? Yes?
In that case, I think that streaming access will be slowed down more because anyway, in the first case also random access, they access the time taken. Then if we are prioritizing that also, if we are not prioritizing that also, we don't see much difference in streaming.
Okay. Okay, let me go through the example and see if there's any flaw here. Okay, let's see. So basically this is what we see if we prioritize a random access thread. Streaming thread slows down by 7x. And if we prioritize a streaming thread, random access slows down by 11x. So this is different from what the answer that I've been getting. Which may be true because the assumptions may matter here. So let's take a look at one reason. Because this is a pure case basically. In the pure case, you have memory banks, clearly. If you have random access thread, what does that mean? That means that, let's assume that both threads have 4 requests. Random access thread spreads its requests across banks, right? So the baseline performance of random access thread is actually very much better. Does that make sense? Because it's really exploiting bank level parallels. Whereas if you have a streaming thread, this is what happens. Of course, it's only 4, right? Imagine this being 128 or so. It's not spreading its requests across the banks. It's really banging on a single bank. And basically, that's what's happening. Okay. This is fine. But let's take a look at basically all requests go to the same row. It has higher overflow locality. Now let's take a look at the case where the streaming thread is prioritized over the random access thread. This poor guy, unfortunately, has one request that's stuck behind. This is the example that I was cooking up, which we were not thinking of probably. Right. In this example, clearly the streaming thread, the random access thread is much more vulnerable, right? Because one streaming thread can destroy its bank level parallels. Does that make sense? So that's the idea. This is the extreme condition, of course. Once things start varying, not all threads are completely random access versus streaming. But in this case, clearly the random access thread is much more vulnerable. And if you actually do the other experiments, I don't have it over here, but if you actually prioritize the random access thread, you will see that the streaming thread is slowed down by only one request, right? That's what would happen. Okay, if you come up with other examples, let me know. So our conclusion is that this thread is more vulnerable to interference in general. So this paper comes up with a metric that combines bank level parallelism and row buffer locality and assigns a vulnerability factor for different threads essentially. And it turns out vulnerability of a thread is higher if it has very high bank level parallelism and very low row buffer locality. That's the idea. And the vulnerability factor is lower if the thread has no bank level parallelism but high row buffer locality. Okay, you can read the paper for more detail. Okay, I think the paper already has this, and I already said this. So there's a niceness metric, and a thread is nicer if it has high bank level parallelism, and less nice if it has high row buffer locality. This is actually in line with the Bliss idea thread. If you're implementing Bliss, you will see that a thread that's actually banging on a row is deemed to be causing interference, and it's blacklisted for a while. Except Bliss doesn't think about bank level parallelism, which is actually a shortcoming of that work, in my opinion. But you want to be simple, right? We had simplicity in that case as well. So once you become more complicated, once you start taking into account more metrics, you become more complex, clearly. Okay, any questions? Everybody's okay with my example? Okay, yes? Yeah, so basically what, that is true, but if you actually have many more requests, like 128 requests to the same row, then you will see the situation. So basically, you're right. It really depends on how many accesses you're making to a given row.
And also, like when we are like having any streaming data, like generally we try to make word level interleaving so that we can have
So that's right, exactly. So so there was another assumption over here. Basically, the interleaving is really row level interleaving. Not you're not interleaving cache blocks across different banks. If you interleave cache blocks across different banks, the streaming access thread looks like a random access thread, because it's not a random access thread, but it really has high bank level parallelism in that case. So there's something we didn't talk about, which is really the interaction between data mapping and scheduling, which is actually an important area. We talked about data mapping at some point briefly, but not to this level of detail. So how your data is mapped into your banks, into your channels, clearly matters in terms of how much interference is happening, as we will see in the data mapping later on. Okay. That's why it's really important to actually lay down your assumptions. So there was an implicit assumption here saying that your row, basically you're interleaving rows across different banks. When you access consecutive 4 kilobyte chunks or 8 kilobyte chunks are actually in consecutive banks. You could actually change that mapping, and you could ensure that consecutive 64 byte chunks are in consecutive banks. In that case, your streaming thread has actually a very high bank level parallelism. Okay, before I go into this, I will say one more thing on that topic. This is actually a very complicated problem, optimizing mapping and scheduling at the same time. And I do not know of any work that has actually done a great job. This is another area where machine learning could be a good place, at least to understand what happens in terms of different choices that we have in terms of mapping and scheduling. Because scheduling itself is very complex, as you can see, right? Remember, when I motivated scheduling, we talked about self-optimizing memory controllers. I still believe that those are very good. All of this work is very, very interesting. But these are all heuristics that humans have developed. And humans have limited thinking. We cannot think about all of those state spaces clearly. This gives us insight into what might be useful to include. But I think once you add one more dimension to the problem, which is mapping, like how your data is mapped, now it becomes really insurmountable. It was already insurmountable, but it becomes doubly insurmountable to me. Because it's another dimension that you need to think about, right? You're not operating just with your scheduler, assuming some mapping. You're changing both at the same time. And ideally, you would like to change both to get the best system, right? You cannot just assume I have this mapping and I want to implement a scheduler. You could do that, of course, for practical reasons, but you may not get the best performance that way. You really want to explore the design space such that you have scheduling algorithms and you have mapping mechanisms, and you really want to explore both of them at the same time to get the highest performance. So your comment's actually pointing to something that's very limited, limiting all of these works, which is really, they don't really consider all of these different interactions because they're so hard to consider for humans, I think. Make sense? That sounds like a bleak thing for human designers, but I think as systems become more complex, design will become more complex also. Okay, so let's take a look at quantum-based operation here. This is similar to Atlas, basically. We're assuming, again, this is another assumption that we make, thread behavior doesn't change significantly between different quantums. So you figure out what's happening in the previous quantum, and you apply what you figured out in the next quantum. So during the previous quantum, you monitor the thread behavior, you figure out the memory intensity, bank level parallelism, and row level locality of each thread. Clearly, we're counting a lot of things here. At the beginning of the quantum, you perform clustering. You compute the niceness of intensive threads, which takes time clearly. And during the quantum, you basically have a shuffling interval where you shuffle the thread ranking for the memory intensive cluster. And in this case, we use 1,000 cycles. You can see that the thread ranking is shuffled at a very fine granularity. Okay. And in the end, this is like any scheduling algorithm, this is also a prioritization order. The highest priority goes to highest ranked threads. Requests from higher ranked threads are prioritized over others. And this means that non-intensive cluster has priority. Within the non-intensive cluster, you have some sort of priority, as we discussed. And within the intensive cluster, you obey the rank shuffling. Again, this is a prioritization order. And all else being equal, you prioritize row hits, and all else being equal, you prioritize all the requests. So this is the FR-FCFS part, except this part almost always takes precedence over FR-FCFS. Okay, and there's some analysis in the paper. Even though storage cost is not high, which is true actually, the implementation cost, the logic cost of this is actually very high, because there's clustering that you need to do, there's other stuff that you need to do, ranking that you need to do. And those costs are quantified actually in the Bliss paper that you're implementing. Okay, so I think I'm going to skip these because we've already discussed all of these algorithms. So let's take a look at the results. Basically, it turns out this kind of gives you the pretty optimal behavior for these workloads. So I qualified with for these workloads because once you change the workloads completely, you may get a different picture. TCM may not be the most fair, for example. PowerBS may sometimes become more fair, depending on your workload. That's why these are all very much workload dependent. And that's why I wanted to present the reinforcement learning memory controllers early on, because humans are very bad at designing policies, or maybe I'm very bad at designing policies that are not good at adapting to workloads. And I think this is true. I've seen this in many works. For some workloads, your policy may be great, but once you change the workloads completely, your policy changes. Or how good the goodness of your policy goes down. And I think this is fundamental. It's not very easy to design a policy that's good for all workloads and workload phases. It's much better to have something that can adapt itself over time, because these are not adapting themselves, right? The policies are still fixed. But for these workloads, TCM is good, as you can see, and it's because it's really exploiting heterogeneity. And it turns out there's something interesting that we also did in this work. We basically looked at the configuration parameters of different policies. For FR-FCFS, for example, it's a cap mechanism. For STFM, it's the unfairness threshold. You can vary those, and you get some sort of behavior in the fairness performance trade-off space, as you can see over here. RBS, you change the marking cap, for example. In Atlas, I think we changed the interval size. In TCM, for some values of cluster threshold, you get nice behavior like this. Basically, you get, it's not true for all values of cluster threshold, but as you vary the cluster threshold, you basically have a good trade-off between fairness and performance. But again, this is also not true for every workload. This is an aggregate across the workloads that we examined. If you look at a single workload, this may not be true. Okay, so it provides fairness throughput trade-off. And all of the other algorithms actually had some operating system support that I didn't really discuss, but clearly for your system, for your memory scheduler to be configurable, you want some sort of operating system support where the operating system can decide some of the thresholds that you have. In this case, cluster threshold is a tunable knob, and operating system can trade off between fairness and throughput. Also, you want to enforce thread priorities or thread weights. In this case, for example, the operating system can assign weights to different threads, and if those weights are communicated to the hardware, to the memory controller can enforce thread weights within each cluster. And for example, how do you enforce thread weights in the memory non-intensive cluster, or memory intensive cluster? Let's say memory non-intensive is easy. In memory non-intensive cluster, you prioritize the threads that have higher weights. In the memory intensive cluster, you want to give higher ranks to threads that have higher weights more often, essentially. That's the idea. Basically, you change the ranking algorithm such that it takes into account the weights that are assigned by the operating system. Does that make sense? I think this is all very important to do, except we're not there yet in the design of memory controllers. As far as I know, none of the memory controllers have thread weights that are communicated to them today. Although, as we will see, in some SoC controllers, you have some other notion. Especially if you have hardware accelerators, you will see that the deadlines are communicated to the memory controller, and memory controllers actually respect some of the deadlines. They try to prioritize requests from hardware accelerators that have a deadline that's coming up soon. We will talk about that. That's a different case. Here, we're talking about more general purpose cores, right? Okay, so let me conclude, I think. I think I already discussed. Basically, none of the previous scheduling algorithms provide both system throughput and fairness because they use a single policy. And the key realization in thread cluster memory scheduling is you want to use different policies so that you can accommodate different types of threads. And different types of threads In this case, you can cluster the threads into 2 clusters, and we already discussed this, so I'm going to skip these. Essentially, you can achieve the best of both worlds if you're able to have a heterogeneous and as a result more complicated memory scheduling calls. Of course, you can generalize the idea and have 2, 3 clusters, 4 clusters, 5 clusters, but things become more complex as you keep going down. If you remember in tiered latency, I like thinking about analogies between different ideas. In tiered latency DRAM, for example, you had 2 different portions of the memory subarray, right? You could again have 3 portions, 4 portions, 5 portions at different levels of latency, capacity trade-offs. But things become more complex as you keep adding different portions or different segments. Any questions about TCM? Maybe you can come up with a better policy. I find all of this fascinating. I think it'd be nice if someone actually incorporates a lot of this quality of service level thinking to machine learning based schedulers. Okay, so the upsides here, this provides both high fairness and high performance. Until this, there was no scheduler that could take on both truly, I think. It caters to the needs for different types of threads, latency versus bandwidth sensitive. Actually, even if you don't implement exactly what's proposed here, having different types of clusters is a good idea in general. Actually, I've seen a lot of SoCs do this. Basically, they somehow try to group threads into latency versus bandwidth sensitive. And they basically, I don't want to say isolate, but they basically treat them differently. They don't do it exactly the same way that we discussed over here. They don't do ranking, but they do prioritization of latency sensitive threads over others, usually. So basically, catering to the needs of different types of threads is a good idea. And it's relatively simple compared to STFM, but it's much more complex compared to Atlas, for example. So it has a bunch of downsides. As you scale the buffer size, it turns out this becomes not so scalable because the algorithms for clustering and ranking become more complex. And as I mentioned earlier, clustering is not very robust. If you don't do a good job over there, some heavy threads can sneak into the non-intensive cluster, and that destroys your fairness. Shuffling is also, as you can see, there are a lot of moving parts. Moving parts meaning that there are a lot of heuristics that you need to decide, and they all need to work nicely. And you may optimize those heuristics for some workloads, but if your workloads don't like those heuristics, then your algorithm becomes not so robust. Okay, and ranking is still too complex, as we also mentioned. Okay. So let's go into blacklisting, and then we'll take a break. How many of you have read this paper? Not yet. How many of you have implemented it? Okay. Is it easy to implement for those who implemented it? Is it easier than Atlas? Yeah, I definitely see heads like this. Yeah, I think so too. I mean, I don't blame you thinking that way. It's always good to strive for these easier solutions, I think, especially after you develop maybe more complex solutions. And the realization here is that basically ranking is not neither scalable nor easy to implement. So let's take a look at, let's take a step back and look at the previous algorithm. Basically, we've been talking about application-aware or thread-aware memory scheduling. Essentially, this has multiple steps. But first, you monitor application behavior, and applications are different. Or threads. I use application and threads interchangeably. You can also add virtual machines over here. Basically, you can keep track of this at different granularities. Again, we're not going to go into that. And then, once you figure out the thread's behavior, you rank the threads according to some criteria, and you enforce the ranks. Basically, these are 3 major steps employed by ranking-based or application-aware schedulers until Bliss. And ranking looks like this, basically. You have a request buffer, and you have some application IDs, and you basically you figure out what is the highest ranked application ID by doing some comparisons. There may be simplified ways of implementing this, and that's true, but at a higher level, in a more pure picture, you basically try to find the request that has the highest ranked application ID. And then you prioritize that thread. And you can see that fundamentally, this is complex, because you have a lot of comparators. Maybe you can use a lot of heuristics and you can simplify this logic, but still, you will need to figure out the request that has the highest ranked application ID. Its latency is also high, but you could also do it earlier, before. So there are a lot of tricks that you can play, but it's clearly, all of those clearly add to your design complexity. So essentially, the realization is that this pool ranking of applications increases critical path latency and also area, chip area significantly to improve both system performance and fairness. The question is, can we do better? Can we do better? Now we're adding another dimension. We want performance, we want fairness, but we also want simplicity. Can we get a better? Can we get to a better point in this multi-dimensional trade-off space? So we have these 3 dimensions: fairness, simplicity, and performance. Ideally, you would like to maximize all of them, right? So these are pictorial. If you look at first ready, first come, first serve, it's bad at performance, bad at fairness, but it's very simple. So it's application unaware. But you don't want application unaware. Okay, we already discussed that. If you look at application aware policies, they look like this. They give you different points in this chart. But essentially, they employ ranking, and they're complex. In the simplicity space, they're actually this way, as you can see. And then the question over here is it essential to give up simplicity to optimize for performance and or fairness? And Bliss actually solves that problem. It basically gives up some performance and fairness. Actually, this is, in terms of performance, it's good. But again, these are all workload dependent. Keep that in mind. When you implement your Bliss, and if you don't test it with a large variety of workloads or with the right workloads, you may find out that its performance is not as high as what you see over here maybe. Its fairness is not going to be as high, but its simplicity going to be almost as close to FR-FCFS. So what's the idea basically? Of course, if you want to achieve this, it's good to develop some ideas to achieve this, right? What is the idea? The observation is that it turns out you don't want this full ranking, especially if you want to be simple. It's actually sufficient to separate applications into 2 groups rather than doing full ranking. So we monitor applications and we rank. We want to eliminate that complexity. Instead, we want to group the applications as vulnerable versus interference causing. That's the idea. And then prioritize the vulnerable applications. The question is, of course, how you do that. So you need to have an idea to be able to do that. And this gives you a benefit of low complexity compared to ranking, because now you have only 2 groups as opposed to n ranks, where n is the number of threads. Right? And it turns out this gives you lower slowdowns ranking also, because ranking is actually very hard to get right, in a sense. How do you actually decide the rank? Why do you actually prioritize thread 4 over thread 3, for example? Maybe sometimes you should prioritize thread 3 over thread 4. That's why the shuffling actually makes ranking a little bit better. But even shuffling is not great, because whenever you shuffle ranks, you give a time slot for a thread to be prioritized during that time slot, but that thread may not have requests during that time. That's another thing that we didn't discuss, but a thread may become high priority, but it may not have a request at that time. So it actually loses the time slot where it's ranked highly. This is always a problem with scheduling techniques. You may be ranked highly, but you may not have a request at that point in time. So there are a lot of issues with ranking, actually. I could go on and on. So eliminating that complexity enables better performance as well sometimes, as you see in this work. So the key question is, of course, how do you form this ranking? So there's another realization in this work that we didn't really write down well, I think. But the idea is, if you actually keep the ranking around for too long, it's not good for performance on performance, because threads change behavior sometimes. Whereas if you actually shuffle, not shuffle, I don't want to use the word shuffling. If you actually are able to swiftly adapt your grouping to the current demands of the applications, then you can adapt to the demands much more quickly. And that's the idea. The Bliss idea is very helpful in that regard. Basically, the second key observation helps with that. If you're serving a large number of consecutive requests from an application, actually causes interference. And that's the idea. Basically, if a lot of requests are served from an application, consecutive requests, we kind of think of that application as something that's interfering with others. This may or may not be true. Right? But basically, we group applications with a large number of consecutive requests as interference causing. They're blacklisted for a while because they've gotten their request serviced, and they may have interfered with others. And even if they didn't interfere with others, they have gotten their request serviced at this point in time. That's the idea. So they're blacklisted for some time. So we deprioritize blacklisted applications for a given amount of time. So there's a threshold over here, which is a bit unfortunate. How long do you deprioritize those applications? And we clear the blacklist periodically. It's relatively quick. basically thousands of cycles as opposed to millions and millions of cycles. And that enabled this grouping to happen very frequently based on application behavior. So that's the idea. Basically, there are multiple benefits. Clearly, it's lower complexity because you just need to figure out which applications have a large number of consecutive requests for some definition of large. And you have only 2 groups, and you basically need to clear these blacklists. And it gives you finer grained grouping decisions, so it leads to lower unfairness and relatively better adaptation to quickly changing application requirements. And as you can see, the results are not bad in the end. I mean, we're not close to the ideal, but it turns out this gives you the highest performance on these workloads. It's closest to fairest, but it's not the most fair, as you can see. And it's closest to the simplest, but it's not the most simple also. So there's a trade-off. Okay, so let's take a look at some results. Hopefully you're seeing this when you read the paper also. But basically it's a very similar graph that I showed you earlier. This is, where are the names? What happened to the names? Okay, anyway. That's why I like the names over here, because now I have to map the this color to over here. But basically you can see that blacklisting over here is close to ideal, but it's not the most fair. It turns out in this case, for example, FR-FCFS is the most fair, and FR-FCFS cap happens to be more fair, very fair also. Yeah. So this is another example of where things are very workload dependent, as you can see. And unfortunately, there is no great methodology for figuring out what are all the workloads, right? We're back to the simulation lecture, in a sense. Or back to the very first lecture in architecture. You have all these workloads in the world. Which ones should you optimize for? Right? That's why I think specialized architectures help that problem a little bit. If you specialize your architecture to some workloads, then you can basically compare more easily, whereas in this case, the workloads are different also. And workloads are changing over time. So it's very hard to compare architectures if that's happening. Okay. I think I already discussed this. So let's take a look at complexity actually. This is actually interesting. This is something we did not talk about as much, but this is also important. And take this with a grain of salt, because these are not the most optimized version of all of these schedulers. If you want to really optimize all of these schedulers, it will take some time. And people actually spend a lot of time to optimize their own schedulers. And they still find new ways of optimizing schedulers. But ideally, you would like to reduce both area and critical path latency, clearly, right? And it turns out FR-FCFS is closest to ideal. It's animating. And you can see that FR-BS is not so good, right? At least in this implementation. These are RTL implementations. And you can see that Atlas is actually good, but not as good. And TCM is over here. I believe FR-BS can be optimized actually even more. But you can see that blacklisting is actually close to the ideal over here also, although not as good as FR-FCFS. So compared to TCM, for example, it gives you much better area and much better critical path latency. And actually, there's a trade-off, I think. You can make, okay, I don't have this bar over here, but there's a bar over here that basically says this is the cycle time that you should have if you actually want to generate a request and keep up with the request bandwidth that you, command bandwidth that you're supposed to have in a particular DRAM technology. And some of them don't satisfy that. I believe that you can actually always design something that can satisfy that by trading off more area such that you can reduce the latency. So this picture is missing some dimension, which is if you actually optimize an implementation, you can potentially reduce the critical path because you make decisions quickly by keeping around more information. Right? And if you want to keep around more information, your scheduler area increases. This is based on experience. It's not on this graph, but there's a trade-off between area and latency. And you've seen this trade-off between area and latency in DRAM, for example. It's a very fundamental trade-off. You can reduce, assuming you have a reasonably optimized design, you're not wasting area to begin with. You can reduce your critical path by adding more area, by adding more bookkeeping information, so that you can access that bookkeeping information much more quickly as opposed to computing them on the fly. Okay. Okay, hopefully you're having fun reading the paper. And this is the longer version. Any questions? No questions? Is this more intuitive than other papers?
not so. I think all of these are intuitive, but they really target a different type of thinking. I don't think there's a single best scheduler. I cannot say that if you give me all of the workloads of the world, one of these schedules will work the best. There will be cases when one of the schedulers, one of the even worst schedulers so far, FR-FCFS for example, will work better than others. And we will see that actually in a little bit. Okay, so I think we should take a break right now. Let's take a break until, let's say, 1:40. So let's continue our journey on memory interference. Now we're going to talk about some more complex systems. Even though we haven't solved the problem with simple systems, the systems are more complex and people need to design memory controllers, right? As a result, we need to talk about more complex systems. And this is basically looking at systems where you have a CPU and GPU together. And these systems exist. And it turns out once you have heterogeneity in the compute units in this sort, you need many more request buffers because GPUs are actually extremely intensive in terms of memory access rates. And it turns out, again, the prior application of our memory scheduler designs are hard to scale to large request buffer sizes. Think about TCM, thread cluster memory scheduling, and also PAR-BS actually. These are not easy to scale. And CFM, I'm not even talking about that because that's very complex. And the solution in this paper has multiple ideas. It's actually has ideas that are orthogonal to everything else we discussed also. Basically, the goal here is really to simplify the scheduler as well as get good performance and get good progress between CPU and GPU as well as add configurable. And the idea is to decompose the memory controller into 3 simple stages. This is really a multi-level memory controller now, as opposed to having a single monolithic scheduler that makes all the decisions at the same time. You make multiple decisions at different levels. And the first one, for example, forms batches of requests that go to the same row. The goal here is to maintain row buffer locality. The second one schedules these batches. It's a scheduler. And the goal of scheduling here is to reduce interference between applications, including CPU cores as well as CPU and GPU. And the last one is a simple stage. It's essentially FIFO queues, first in, first out queues that go to different banks, and they basically simply issue requests to DUN. So essentially all of the scheduling is really done between 1 and 2, and the command scheduler is kept really simple. The function of this last one is really correctness, because it's really first in, first out. The function of these two are performance at low complexity, again. And it turns out this is significantly simpler and more scalable. Maybe not necessarily the best performance, actually, under all conditions, but we will see that on average it gives you good performance. Yeah. So let's take a look at the problem. Basically, the problem is these purple requests are all from the GPU. Essentially, the GPU is very intensive, much more intensive than many many applications that are over here, because this has many cores, right? And the applications are such that you're accessing memory a lot. And the idea is that this memory scheduler over here will be replaced with three-state memory scheduling. The first one forms the batches. And I'll give you the basic ideas. I'm not going to go into the details over here. But the one big basic idea is really having a multi-level scheduler as opposed to a single monolithic scheduler that makes all the decisions is much more simple. That's the first thing. We will see some results with that. Then the question is, what do you do in each level? In this particular case, in the first level or first stage, we do the batch formation. In this case, batch refers to a batch of requests that go to the same row. It's a different batch, basically. Although you could form the batches with some other criteria. That's why we kept calling this batches. The second stage is the scheduling across the batches, across different cores. So you basically have different queues. In these queues, you have batches of requests, and the batch scheduler's job is to schedule those batches to different banks. And the banks have also queues, and these queues are actually, essentially, they look like this. So let's take a look at batch formation. There's some algorithm for it, but basically the goal is to form consecutive requests that go to the same row together. This way you can actually see how big your batches are. For example, GPU usually has very large batches because it has a lot of requests to the same row. So it has very high row buffer locality. It also has very high bank level parallelism, which is not shown here. And if you look over here, there are batches over here as well. You can see that this core doesn't have a lot of row buffer locality. This core has higher row buffer locality, assuming you're forming the batches based on
the rows that you're accessing. And then you can actually treat these requests as, for example, if the batches are formed based on which parts of a row that you're accessing, you could treat these many requests. Let's assume that you have 128 requests going to the same row. You could treat that as almost like a single request. You could kind of compress it, right? You could say that I have a batch of 128 requests that go to the same row. And then I have a batch of 5 requests that go to the same row. I have a batch of 1 request that go to the same row. Now the scheduler's task is to pick between those batches. And then it has a mechanism to pick between those batches. Then you're dealing with batches now. You're not dealing with individual requests. That's an interesting part, because that also gives you opportunity to reduce complexity, because you're not dealing with every single individual request that go to the same row, right? Even though they may go to the different cache lines. Okay, so basically, this batch scheduler can have multiple policies implemented. We basically experimented with 2 in this case. One is shortest job first, meaning the shortest batch first. You prioritize the batches that are the shortest over here. And the other is, in this case, you prioritize that one. And then you can switch to round robin also. Round robin meaning you go round robin over here. So it's trying to actually get the best of both worlds in terms of performance and fairness again, right? You have 2 different policies that you pick from over here. And we have a probabilistic mechanism to select between the different policies. So depending on how your system is doing, you can pick between shortest job first and round robin. Make sense? So shortest job first is clearly not good for the GPU, right? It's more, as we've seen with Atlas, it's more a policy that's good for latency sensitive workloads. And if you have a latency sensitive core over here, shortest job first is good. Round robin is actually not bad for GPU and not bad for fairness also. But it's not good for these latency sensitive applications. So you basically switch between these 2 policies. But again, this is a framework where you could plug in other policies as well. I don't think this is the best implementation of the framework, really. Okay. And then the last stage's job is really to schedule the requests that go to the main. So that's the level of detail I will go into in this one. You got the high-level ideas. So let's take a look at the complexity. So complexity actually, it turns out, is very good in this case, compared to even a row hit first scheduler, which is first ready, first come, first serve, right? Which is the simplest scheduler. This consumes less area and less static power, which is interesting, right? Because first ready, first come, first serve is also complex if you scale to very large buffer sizes. So the reduction really comes from multiple things. You have a monolithic scheduler, and you take it, you break it into stages of simpler schedulers. Each scheduler is simpler. Each scheduler operates on a smaller number of requests, let's say, as opposed to having a single scheduler operating on many requests at the same time. And also you reduce the complexity because you're not dealing with every single request. You're dealing with batches. Makes sense? You're coarsening the granularity basically of requests, assuming you have large batches. Now you can also, each stage is a simpler scheduler. Each stage considers fewer properties at a time to make the scheduling decision. For example, the top stage, batch formation, looks at row buffer locality only. You could add more to it, but it just looks at row buffer locality. Whereas if you look at TCM, for all of the requests, you are looking at many things at the same time. RBS also, similar. Now you can actually customize each of the simpler schedulers also for that scheduling decision. Each stage also has simpler buffers. For example, the last stage is FIFO. The first stage is also like FIFO. There's some limited amount of reordering, first in, first out. Middle part is really a scheduler, so there's no notion of FIFO over there. But now you can make the buffers simpler as well, as opposed to have many buffers. And also each stage has a portion of the total buffer size. Buffering is really distributed across stages. So if you have an equal buffer size comparison, this is definitely simpler. And each stage is also simpler, as we discussed. Any questions on this? So this is the advantage of having a multi-level design as opposed to a single level design. And with a lot of optimization, there's also another thing that I didn't discuss, but this enables you to trade off. This enables you to input importance of the GPU, let's say, into the system. For example, if the GPU is running something time critical at that point in time, if it's rendering some frame and you're close to the deadline, for example, you could increase its weight. If the GPU is not running something that's important, you could reduce its weight, and you could the scheduler adapts to what's happening in the multi-core. And this is actually the best previous scheduler according to our experiments for different importances that are assigned to GPUs. If the GPU is not important, it turns out Atlas is the best scheduler for performance because it really prioritizes the latency-sensitive applications. But if the GPU is actually somewhat important, TCM is the best scheduler. This is kind of somewhere in the middle, as you can see. GPU weight kind of indicates how fair you should be, right? System performance is not the only thing that you should really care about. But if GPU is really, really important, it turns out FR-FCFS is the best policy. And this kind of gives you an idea of the dependence of your policy to the workload that you're executing. In this case, workload is not varying. It's really running the same thing, but the importance is changing. And this makes also sense because if the GPU is really important, GPU has very high row-buffer locality, and FR-FCFS is really great at exploiting that row-buffer locality, more than any other algorithm actually. So that makes sense in this case. So if the GPU is really important, you really want to employ FR-FCFS. So this also makes a case for switching between different policies, right? You may actually implement all of these policies and switch between them. But I think that's very clunky in terms of a hardware design. That basically increases your complexity in terms of hardware. You need to design all of these policies and verify them and figure out a method for switching between them also. I don't think that's a good solution. So SMS state memory scheduling tries to approximate that solution without switching between the policies, and this is the result that you get basically based on the algorithm that I briefly glanced over. Essentially, you get better performance or similar performance to the best previous scheduling. Here you're tracking, if the GPU is really important, you're tracking FR-FCFS. If the GPU is not important, you actually have a better policy than the best previous policy. Okay. And if you're interested, you can read more about this. Okay. But it's good that you're not implementing it because it's also complex. Even though the overall complexity is low, you need to think about a lot of these different components, basically. Okay, so let's go into a little bit more into state of the art. I'd like to give you a flavor of what really exists in an SoC like this. The problem is actually more complicated than we've been discussing, basically. We've been working on, even though these are actually really, really interesting ideas, they only cover part of the space. So the space is actually like this, basically. You have CPUs and hardware accelerators, and GPU is one sort of hardware accelerator as well. So the question is, you really need to deal with hardware accelerators as well. Actually, this is a picture from the paper. It's more complicated than my earlier picture. In an SoC, you have something that looks like this, basically. The DRAM is really kind of the memory controller is really kind of the access control point to memory, and essentially everything over here needs to access memory. And you can see that clearly there are cores over here, which we've been dealing with. There's a GPU over there, which we've kind of been dealing with also with the previous work, but there are also DSPs. There's video, audio accelerators. There are DNA engines. There are a bunch of other stuff over here. There's even modem over here, right? And you really need to make sure that all of these get access to memory. And they may be requesting memory at the same time. So the problem is more complicated, clearly. So this scheduler actually, it's a complex scheduler, but it's trying to tackle that complicated problem also with heuristics again, right? And the problem it's trying to solve is that, and I'm going to treat all of these as hardware accelerators. GPU is a hardware accelerator also, right, for certain programs, except it's a very special hardware accelerator that is used increasingly by more general purpose programs also. Okay, basically, in a system like this, hardware accelerators and CPUs share the same memory subsystem and they interfere with each other. And the goal was to actually design a memory scheduler that improves CPU performance while meeting the deadlines of the hardware accelerators. And these different hardware accelerators have different deadlines. Some of them actually have very short deadlines. They need responses very quickly from memory. Some of them can tolerate, can have long deadlines. As long as they have some requests satisfied across those long deadlines, they're happy. And these deadlines clearly affect the user, right? If this doesn't render a page in time, then I get affected, for example. As we discussed, different hardware accelerators have different memory access characteristics as well as different deadlines. So it's not just the different deadlines, but they also have different memory access characteristics. A lot of them are very streaming, but some of them have random access properties too. And current schedulers do not smoothly handle these. Again, I'm not going into a lot of detail over here because the system is relatively complicated. I'll give you the basic ideas. So basically, one of the approaches to this is what people have done in an SoC, for example. They keep track of, usually in a hardware accelerator, you know how many requests you're supposed to service until your deadline. So you have some sort of bandwidth requirement or latency requirement. Bandwidth is easier. You can basically keep track of how many requests you've serviced so far. And you know how many requests you're supposed to service until your deadline ends. And you can prioritize the hardware accelerator accordingly. As long as you service, for example, 10,000 requests in 1 millisecond, the hardware accelerator meets its deadline. Make sense? Now you can input that to the memory scheduler, and most SoCs input that to the memory scheduler today, good SoCs. SoC is a system on chip. I like defining these words, but sometimes SoC is used a lot. I guess there were two SoC conferences. One is called SoCC, and one is called SoC. The other is also called SoCC. Can you guess what those are? System on a Chip conference, that's one. The other one is Symposium on Cloud Computing. So both of them are the same, but they're very different. So if you don't define what it is, you may actually go to the wrong conference. Hopefully you'll learn something, but it may be the wrong conference. Okay, so basically what these memory controllers usually do is they try to track how many requests are being serviced, and at some point they raise the priority of the hardware accelerator. Meaning they prioritize the hardware accelerator over everything else so that the hardware accelerator can meet its deadline. And they don't do this very smoothly for whatever reason, for the reasons that you can read in the paper. And that's the idea basically. These memory intensive and long deadline hardware accelerators can significantly degrade CPU performance when they become high priority. So if you don't handle these well, they made very little progress for a long time. And closer to their deadline, you increase their priority. And these have a lot of requests to send, which means that they're delaying everything else in the system. Right? So you need to handle them more smoothly. Basically, this paper proposes a way of handling them more smoothly. And also, short deadline hardware accelerators sometimes miss their deadlines despite high priority. This short deadline accelerator, it needs to get a small number of requests serviced within a microsecond, for example, for whatever reason, right? You may need to detect an image very quickly. That's an example. And sometimes they miss their deadlines if you don't handle those cases very well. And these cases are very hard to handle because if you have a lot of requests that are already queued, if you have a scheduling algorithm that doesn't adapt very quickly, even if you may give these short deadline accelerators high priority, they may miss their deadlines. And the paper examines some concrete cases. So the solution in this paper is what's called Dash Memory Scheduler, Deadline Aware Heterogeneous, something like that. I don't even remember what it stands for. But Dash sounds good, right? But basically, you prioritize hardware accelerators over CPUs anytime when the hardware accelerator is not making good progress. I think that the first idea is very simple. It's almost like common sense, right? As opposed to raising the deadline very close to, raising the priority of a hardware accelerator very close to the deadline, you keep track of its progress, and you basically ensure that it's making proportional progress to its deadline. So if it's supposed to satisfy 10,000 requests within 1 millisecond, even in a finer interval, you look at, let's say, 1 microsecond, it's supposed to make proportional progress to 10,000 requests within 1 millisecond, right? Does that make sense? You basically figure out how many requests you're supposed to send to make proportional progress within 1 millisecond, given your 10,000 requests within you figure out how many requests you're supposed to send within a fine-grained interval, given your coarse-grained requirements, and you try to ensure that you send those requests within fine-grained intervals. That's the idea. Basically, you keep making proportional progress so that you don't need to raise your priority at the end. I think of this as common sense, but it turns out this sometimes it's not easy to design these things. And the second idea is to have application-aware scheduling for CPUs and hardware accelerators. Basically, you have thread-aware scheduling that tries to prioritize latency-sensitive ones over bandwidth-sensitive ones. And it turns out the results are good. You improve both performance here, as well as you meet all of the deadlines. It turns out baseline schedulers sometimes miss the deadlines. Okay, and you can actually experiment with this on your own. I'm going to skip this one. We already talked about this, I think. So these are extra slides. So this is what I was saying basically. You want to distribute the priority for accelerators. You don't want to do worst case prioritization, meaning say this is when I'm supposed to meet my deadline, I'm going to send my request right before I meet my deadline. That's some sort of worst case prioritization. Right? Basically, prioritize when the hardware accelerator is not on track to meet a deadline. And you distribute the priority over time as opposed to doing it in the last moment. Basically, the idea is don't procrastinate. I think this is useful for studies as well, right? If you procrastinate, you may not meet the deadline because you may have too much to study right before the exam. Whereas if you study in a distributed manner, you can actually meet your deadline, right? That's why it's common sense, I think. Of course, you may not always employ that, right, as students. I know that also, I've been there. You may not always be able to do that, clearly. That's why it's a hard problem here as well. It's not only procrastination, it's also there's something else that's happening, right, that you need to do. Okay. No. Okay, so there's also this observation, which is not all accelerators are equal. There are some accelerators that have very long deadlines, and they're more likely to meet their deadlines, although they may interfere with others a lot. Short deadline accelerators are more likely to miss their deadlines. So the idea is to schedule the short deadline accelerators based on worst case memory access time. Here, you again know, the assumption is that you know how many requests that you're going to send within a time interval. You basically figure out what is the worst case scenario. Meaning, if you're delayed in the worst case, assuming you prioritize this accelerator, how much time do you need? And you start sending the requests at that point in time, basically. That's the idea over here. But of course, this depends on the assumption that you know how many requests you're going to send. And in most accelerators, you have an idea. For example, in a GPU, if you want to refresh the frames, let's say it's 60 frames per second, right? Or 30 frames per second. It's increasing, but 60 frames per second is, you can calculate the number of memory requests that you're going to send based on that higher level requirement. And you may have similar requirements in terms of audio, in terms of detection of some image, because you know the size of the image, and you know the processing requirements, you know the memory access requirements. You can basically calculate a lot of the requirements that you have in terms of the memory access speed for these accelerators because they're specialized. You cannot do this in a general purpose core. Okay. And also the next observation here is, we already know this actually, not all CPU cores are equal. This work realizes and applies it to an SoC system. Basically, the idea is memory-intensive cores are much less vulnerable to interference, and memory-non-intensive cores are much more vulnerable to interference, as we've seen. If you have a request that you generate once in a while, you're more likely to be delayed, clearly, by something more intensive. So in this case, the idea is to prioritize the accelerators over memory-intensive cores, because memory-intensive cores are very heavy, so that these accelerators do not become urgent. Urgent meaning high priority at some point in time. Okay, so basically these are the key ideas over here. I think distribute priority for hardware accelerators as opposed to making them prioritize at the very end of their deadlines. Prioritize hardware accelerators over memory-intensive CPU cores, even when those hardware accelerators are not the highest priority things, so that they can actually keep track of their priority. And prioritize short deadline period hardware accelerators based on worst case estimates, as we discussed. And the results look good. I'll give you an example of the scheduling policy. Basically, it's not an easy scheduling policy in the end. Again, it's a human design scheduling policy, as you can see. And we don't necessarily make the right choices. So we have a mechanism over here that can switch probabilistically between these, because it's not clear how you order these things. Again, you're a human, you're designing these things. Do you prioritize a long deadline period hardware accelerator with low priority, or a memory-intensive CPU application? With low priority meaning it's on track to keep its deadline, so there's no reason to prioritize it. But also a memory-intensive CPU application, is there a reason to prioritize it? Right? So some of these heuristics you need to decide potentially, but then you may not make the best decision. So there's probabilistic mechanism. I actually like probabilistic scheduling mechanisms when you can figure out how you can incorporate the probabilities. I think machine learning does a much better job in terms of probabilistic policies than humans, again. Okay, so this is a scheduling policy based on everything we discussed. Okay, and if you're interested, you can read this paper. And as far as I know, this is really the state of the art in terms of complex CPU, GPU, hardware accelerator scheduling. The paper has an evaluation on GPUs as well. You can take a look at that. As far as I know, I have not seen any work beyond this that looks at this complicated problem. Maybe it's too complex for people to tackle. maybe the next step is really figuring out how to do this with machine learning. Okay. Any questions? Comments? Now you know how to meet your deadlines in the future now, right? You can read the paper, maybe get some inspiration. Okay, this is something I'm not going to talk about because we don't have a lot of time, but this is also fascinating, and I'm going to give you some references very briefly. But basically, the problem is even worse than that. Hardware accelerators is one example of predictable performance. You want to get your deadline satisfied, and that's clearly, you want to have some predictable performance from this definition of predictable performance. But there are other cases where you want predictable performance over here also. Now that problem is more difficult, right? Because here you don't even know how many requests that you're going to service within 1 millisecond, for example. You don't have that bandwidth requirement because it's a general purpose system. But somebody assumes that you're supposed to not be slowed down by so much, right? That's the expectation, for example, right? You're running some application, I don't know what it's doing, but basically it's interacting with me, and I don't want it to be delayed. Because that's the case in the general purpose case. So you really want to allocate resources such that you get predictable performance when you need it for all of these applications that are running in those resources. Right? Sometimes it's easy, sometimes it's hard, but the hardness of this is worse than this, I think. Unless you have hardware accelerators that also become not so easy to quantify in terms of deadlines going into the future. Okay, so I think I'll give you the approach over here, but I'm not going to go in detail. Approach basically builds upon this full-time fair memory scheduling in the end. Basically, we want to somehow estimate the slowdown of an application in the presence of resource sharing. If you don't know anything about an application, bandwidth demand, latency demand, if you have an estimate of the slowdown, you could do something with it. Because now you know this application is slowed down by 10x, for example, because it's sharing resources with others. And now you can use this information to achieve the required performance levels for all applications, assuming someone gives you the maximum tolerable slowdown for their application. Right? You can use the different memory scheduling prioritization mechanisms to actually prioritize the applications that have been slowed down more than they're supposed to be slowed down. Does that make sense? That's the idea. Of course, I'm not telling you exactly how we do it, but that's the idea. And of course, the goal is to really provide high system performance all the while doing so. You don't want to do this by taking out applications from the system. It's easy to do this if you're not meeting the requirements of an application when it's running together with other applications. Get rid of all of the other applications, right? But that doesn't really solve the performance problem. That may solve the quality of service problem. And these papers cover the state of the art, and I'm not going to go through this. Actually, I'm going to cover this one. This also tries to estimate the slowdowns, but doesn't do a great job at it because it uses relatively simple heuristics. Whereas these ones, I mentioned that briefly, basically raise the level of abstraction a little bit. They try to estimate the slowdowns not on a per request basis, but on a coarser granularity, on a request service rate basis. And they actually, this achieves slowdown estimates that are as good as 10%. So the error in terms of estimating slowdown is about 10% across a wide variety of applications here. And this paper takes it even one more step further. It doesn't just look at the memory system, but it also looks at caches. So the problem is actually even more complex, right? If you really want to estimate the slowdown on an application, you cannot just look at the memory controller. You need to look at the caches. You need to look at the interconnect. You need to look at all of the shared resources. You need to look at how things are. Basically, you need to figure out the slowdown across the entire system. And this paper actually looks at how to do it with caches. Of course, there's more complexity here, but you can read it on your own. Any questions? Okay. Now I'm giving you a lot of other dimensions, right? And there's no work that actually solves all of these because it's very complicated. I'm going to add more dimension over here. So far, we've been assuming one thing, right? We've been assuming that threads are not cooperating with each other. The problem becomes completely different, actually, when threads start cooperating with each other. Completely meaning you need to take into account other stuff now. Let's take a look at that. Basically, all of you have written multi-thread applications, I assume, right? How many of you have written multi-threaded applications? Locks, barriers, condition variables, semaphores, at least one of them. Okay, good. And it's a pain, but it gives you performance if you do it well. So far, we have not even talked about synchronization in these applications. And we assume that all of these threads that are executing are independent, and we're trying to estimate slowdowns, we're trying to prioritize. But these mechanisms don't necessarily work if the applications are interdependent. Clearly, this is a different scenario. And these threads can synchronize with each other in an application with very different constructs. And some threads can be on the critical path of execution due to synchronization, some threads are not. So this is actually very important, I think. If you actually prioritize a thread that's not on the critical path, meaning that's not the limiting thread, your memory scheduler is doing something useless, essentially. It's prioritizing some other thread, and you're not gaining any performance because you're really doing the prioritization on the wrong thing. And even within a thread, some code segments may be on the critical path of execution, some are not. Basically, while you're executing some code, you may have many threads, and at some point in time, some part of your code is critical. It's actually even broader than multi-thread applications. Even if you're doing single-thread applications, there are some parts of your code that are more critical than others because of auto-order execution, for example, in your processor. But at some point, some thread, some part of code, some part of thread is critical. And the question is, can you somehow identify that and prioritize that? Of course, if you identify this, you can use it for other purposes as well, right? You don't just use it for memory scheduling, but you could use it for, I don't know, you could execute that portion of the code with higher frequency, for example, right? Because that's more important. So fundamentally, I think this is an important problem. So let's take a look at some of these pieces just to jog your memory. I assume you've covered some of these. But basically, critical sections enforce mutually exclusive access to shared data. You basically have this thread that is updating some shared data within a critical section so that no other thread can access it while that update is happening. And this is a non-critical section. If you look at the execution of this thread, this is a non-critical section. This is a critical section. And only one thread can be executing this critical section at a given time, the thread that holds the lock. If you look at the execution time of two threads, just two threads in this case, assume that thread 2 enters the critical section over here. Thread 1, for some reason, takes longer to get to the critical section. While the thread 2 is in the critical section, it cannot really, the thread 1 stays idle, basically. So for example, if you have a memory scheduler and thread 1 and thread 2 are both accessing the memory scheduler at the same time during this time, prioritizing thread 1 is probably not a good idea. Okay. Prioritizing thread 2 is probably a good idea because it's in the critical section that's really delaying progress. And imagine that this thread may be delaying progress of, I don't know, 100 other threads if it's holding a lock that's needed by the remaining threads. Okay, so essentially contented critical sections. In this case, this critical section is contented because there are threads that are waiting for it. Threads causing serialization can be on the critical path. That's one example. So barriers are another form of synchronization. If you've done barrier-based programming, multi-synchronous programming, for example, programs usually look like this. You compute, each thread does this. You compute something in parallel across different threads, and then there's a barrier that waits, that enables you to wait for all of the other threads to compute, because maybe you're going to exchange some results between the threads, and then you're going to continue parallel computation. And this is the critical part over here. And if you look at just this execution until the end of the barrier over here, if one thread reaches the barrier earlier, it basically waits. You're basically not doing useful work during that time, right? And thread 2 is in the critical thread in this case because it's reaching the barrier later. It's making all of the other threads wait, basically, because for whatever reason, it's reaching the barrier late. So last thread arriving at the barrier is on the critical path. So this could be due to load imbalance, for example, right? For some reason, one thread has more work to do. The programmer didn't partition the work really well. Or for whatever reason, the work didn't have enough computation in it for that particular, for some threads, whereas it did have a lot of computation for some other thread. As a result, this thread reaches the barrier late. But in this case, if you can somehow predict which thread is going to reach the barrier late, you can prioritize it, right? In the memory scheduler, for example. And the idea is to how do you predict that? And I'm not going to give you answers in this lecture. Maybe in a future lecture we're going to talk about this problem. But assuming you know that information, you could design a much better memory scheduler. Okay, so the third example of synchronization that I will talk about is pipelining. This is very similar to systolic arrays. essentially you can statically divide loop iterations into code segments called stages. Let's say this way you can parallelize a loop. So you have 3 different computation phases, and you decide that A, B, C can be executed in different cores. And basically what you do is you execute A's of different loop iterations on this core, B's of different loop iterations on this core, and C's of different loop iterations on this core. Why may this make sense? It may make sense because, for example, A's are accessing some shared data structure, right? You always use, you have good locality across different loop iterations for this A part. You may want to keep them on the same core and basically execute all the A's over here. And the results that are generated by A and B, maybe there are very few results that are generated. The communication may be very low, and you communicate that between A and B through some queues. And B maybe has good locality. B's of different loop iterations may have good locality also. Similarly, C's of different loop iterations may have good locality. That could be locality-based partitioning. There could be other reasons for this. A, B, and C may have completely different computation characteristics, for example, and you may have specialized units for A, B, and C, such that, and then you send A's here, B's here, and C's here, such that they execute most efficiently. We're going to see examples of this later on. Okay, but basically, if this is the case, if this is how you parallelize your program, the thread that's executing the slowest stage is on the critical path. Okay. So basically, let's take an example over here. So thread 1 over here is executing A's, thread 2 is executing B's, and thread 3 is executing C's, somehow. And if you look over here, B takes the longest. And if B takes the longest, it's really limiting the throughput of this execution. It's really basically what happens is at some point A starts stalling because these queues get full and they cannot make progress, and you see this sort of idleness over here. That's true for C's also. At some point, because B is not making a lot of progress, it's not generating enough results, so C's cannot continue, right? Because they don't have the input they need from the previous stage. That's the idea. So clearly there's a critical stage over here, which is B, and if you have a memory scheduler that doesn't prioritize B, then you can actually make this worse. Or this is already worse, because the memory schedulers do not have an idea of what's critical and what's not. Make sense? Have people written programs like this? Parallelizing within a loop across different cores? It's not a very common case, but this is increasingly used in some programs. They're called pipeline parallel programs. Okay. Okay, I think I have a lot of animation here. So basically, what's the idea here? The idea is very simple. Somehow figure out which threads, I think I've already set up these questions. How do we schedule the request of interdependent threads to maximize multi-threaded performance? Somehow figure out threads that are limiting your performance, that are likely to be on the critical path, and prioritize their requests. That's the idea. Once you have that information, which is the hardest part actually, figuring out how to figure out those threads, you prioritize their requests in the memory scheduler so that those threads do not get delayed. And then the key question is, what happens to the other threads? Other threads, you know that they're not critical, or you predict that they're not critical. And this work basically shuffles the priorities of those non-limiter threads to reduce the memory interference among them. Of course, you could imagine other policies. If you have more information, maybe you have a criticality ranking of the threads. These threads are very critical. These threads are kind of secondary critical, and these threads are less critical. Maybe you can enforce that in the memory scheduler also. Okay, so how do you actually estimate the limiter threads? We're going to talk more about this when we talk about heterogeneous multiprocessing, because these ideas are actually estimation of limiter threads are much more generally applicable than memory. You can create specialized cores for these limiter threads, for example. But let me do the high-level idea. Basically, it's a hardware-software cooperative mechanism. I don't think you can do this purely in hardware very, very easily, at least. For example, you want to estimate thread executing the most contented critical section, and this paper used the hardware-software cooperative mechanism for that. Thread executing the slowest pipeline stage. You could also determine that. If you have some information from the software that tells you these are the pipeline stages, you could collect information as to how much throughput you're getting in each of the pipeline stages, and you can basically decide which one is the slowest pipeline stage. It's relatively easy, assuming you have that information, right? Similarly, if you have information about the software saying these are my critical sections, you could count, you could figure out how many times different threads get delayed because of this particular critical section, right? And then you can say, oh, this critical section is really important for performance, and whenever a thread holds the lock for this critical section, I'm going to prioritize. You could go even further. You could try to predict which threads are going to get the critical section, get that lock. But that's a harder problem, actually. People try to predict which threads are going to get the locks so that they can do other optimizations, and that's not an easy problem. Okay? Of course, if you have a runtime system that you're designing together with your hardware, you could do even more optimization. In fact, you could design the runtime system such that it gives the threads, it gives the locks to the threads in a more predictable way, potentially, such that your hardware is simple, right? That could be one way. But once you co-design across the stack, there are a lot of opportunities, actually. Okay, and the last one is thread that's falling behind the most and reaching a barrier. Okay, we'll talk more about these later on. But let me give you an example of how to prioritize these limited threads. So essentially, I'm showing you this thread A, B, C, D over here. This is the full execution time. Clearly, things are easy once you know the full execution at the end, but you're making dynamic decisions without knowing the future. So these are non-critical sections. You can see there are two critical sections, green and orange. And there's a barrier over here. And this denotes that the thread is waiting for synchronization or lock. And the red part that I'm going to show is the critical path of execution. So if you want to figure out the critical path over here, we have to start with a thread that reaches the barrier, the last thread. Clearly, all of these threads are waiting. They're done. They're not on the critical path at this point. So basically, how do you figure out the critical path? This is actually a really interesting thing to do if you're doing analysis of a multi-thread program execution. You basically need to trace back the execution. You basically start with the barrier and figure out the critical path this way. Clearly, I've done it for you over here, but this thread is on the critical path. Here it's waiting. Clearly, it's not on the critical path because someone else caused it to wait. And who is that? It's this thread C. Now this thread is waiting over here. Clearly, it's not on the critical path anymore because someone else caused it to wait, and it's thread B. Here, this thread is waiting. Someone else caused it to wait. It's this thread, so that's on the critical path. Here, this thread is waiting for a while, and someone else caused it to wait, so it's this thread. Same here, same here, same here. That's how you trace back your critical path. Of course, it's easy once you know the full execution time. Key question is, how do you predict this critical path while you're running the program? Not so easy. Okay, but assuming that you have some sort of identification mechanism during this time, let's assume that we somehow identify it at this point, and we figure out that here the most contended critical section is 1, and limiter thread is D at this point, so you prioritize that. And then the limiter thread becomes C over here, because as you can see, the most contended critical section is the green one over here. I didn't say it before, but if you keep looking, for some time you'll figure out that based on these patterns, the green critical section is kind of the limiter critical section. And whenever a thread gets to it, you spend some time identifying that with some mechanisms. And whenever a thread gets to this most contended critical section, you prioritize that thread. And in this case, prioritization is done in the memory controller. So this thread is holding critical section 1, so it gets prioritized. And this thread is holding critical section 1 and gets prioritized. And that way you can save some cycles, as you can see over here. Make sense? But of course, doing this is not easy. And we will discuss how to estimate this most contended critical section later on. But I gave you the basic idea. You kind of count how much waiting a given lock causes to other threads. This requires you to identify what is a lock. That's where software information is very useful. Because in general, whenever you have a lock, it's more like a memory location to the hardware, right? Informing the hardware saying that this is a synchronization primitive is very useful. Okay. And now your critical path is shortened. Okay, without going into more detail, let's talk about any questions so far? I know I haven't given you the identification mechanism, but I've given you the high-level idea. Now you can imagine many other mechanisms of this. Questions, ideas? Okay, let's analyze this at the high level. basically this has a bunch of upsides. It improves the performance of multi-thread applications. It turns out actually using other scheduling mechanisms that we discussed, they don't have this information, right? As a result, they may improve multi-thread application performance, but they're not doing so because they're taking into account this criticality. They're doing so because they're reducing interference between different threads. And not all multi-thread applications are bottlenecked by all of this. So those other scheduling mechanisms are still useful for multi-thread applications, except they may sometimes reduce performance also by doing the wrong thing for threads that are holding these locks, for example. It provides a mechanism for estimating limited threads, and it opens a path for slowdown estimation for multi-thread applications also. Even though this is not done, this is also an open problem right now. How do you actually do the slowdown estimation for a multi-thread application? You have 1,000 threads in your application. How do you estimate the slowdown compared to when the application is run alone, as opposed to when it's run together with some other application in the system? Clearly, it has downsides. It doesn't cover the problem of, maybe it's a limitation, more of a downside. It doesn't cover the problem of multiple multi-thread applications, and that's a common scenario today. You have multiple applications that are, each of which is multi-threaded. Limited thread estimation can become complex, and that's true. And maybe there are other downsides also, but I don't have them here. If you read the paper, you'll figure out more downsides probably. Okay. I think that's the last thing that I wanted to cover with memory scheduling. So if you're looking forward to the end of memory scheduling, this is it. Any questions on memory scheduling? Otherwise, we're going to switch gears and look at more things. No? No new ideas? This is an area where new ideas are desperately needed, I think. Because I know that a lot of people are banging their heads to figure out how to design these memory schedules in a better way. As you know very well by now, that this problem is not getting simpler. It's getting more complex. And it's becoming more important also. Okay, so let's talk about some other ways then, if we're done with talking about memory scheduling. So we're going to talk about multiple things: data mapping to banks, channels, and ranks, and then core throttling, and then if we have time, we'll talk more about application and thread scheduling as well. But probably we will not have a lot of time. Let's start with this one. I mean, I mentioned this multiple times before, but okay. Basically, we're switching to the dumb resource approach. The idea is, can we keep the resources more or less simple, not quality of service aware, but can we do something else around the system? As I said, these things are orthogonal to each other. You can do both at the same time, especially if you co-design the mechanisms. But a purest distinction is keep the resources dumb and do something else. Basically, do better data mapping such that you don't run into interference issues. And this is probably the first paper that introduced this at the channel level. Later, there are works that are at the bank level, at the lower levels. Okay, basically the realization is that we have multiple channels in a modern system, and they provide a new degree of freedom. That they enable us to map data across multiple channels. Right? Now, how do you do data mapping in current systems? Basically, if you have, this is a simplified case where you have two applications and two channels. Basically, applications are memory, or the memory allocator maps the application pages irrespective of the channels. Basically, the pages of different applications are distributed across channels. And this causes interference clearly, because different applications now access the same channel, and they all interfere with each other in all channels. So the question is, can we actually use the new degree of freedom such that we can map an application to one channel and the other application to another channel, and then they all execute happily without interfering with each other? And clearly, if you have two channels, they're completely independent. There is no interference on this part of the system, at least. Because this is, now you're isolating the applications. But of course, this is a simplified picture. You have two applications, two memory channels. This doesn't scale, right? You don't have 1,000 applications and 1,000 memory channels. 1,000 memory channels are extremely expensive. So in the end, you may have more applications over here. You actually have more applications over here than the number of memory channels. So you need to do some sort of clustering if you want to get the benefits of this sort of channel partition. You will not be able to completely eliminate interference. You will be able to reduce it somehow. And also there's another issue over here, which is the Zürich airport problem, right? If you actually do this, what happens if this blue application, for example, needs more bandwidth? Now you're restricting the bandwidth. You're not just reducing interference, you're actually restricting the bandwidth of the applications that are mapped to this channel. So you don't want to do this maybe in a very hard partitioned way. You want to be more flexible. There's also another thing over here. You're also partitioning memory space. Right? If you think of this as a very hard way, this application can go only to this channel and this application can go only to that channel. That may be a bad idea because now you're actually halving the memory that this application can access. What if it needs more memory? Right? Memory capacity. You don't want to do that also. So that's why hard partitioning, we're going to avoid hard partitioning in these cases. We're going to use soft partitioning. Because the trade-off is, okay, I'm eliminating interference this way, but if this application is getting more page faults right now because it doesn't have enough memory and it has to go to the disk, that's much worse, right? You don't want to make that trade-off at all. Okay, so let me give you the overview of this. Basically, the idea in all partitioning mechanisms is to eliminate harmful interference between applications. And the basic idea in this work is to map the data of badly interfering applications to different channels. So then the question is, what is badly interfering? Right? So this work separates, this work deems low intensity applications and high intensity applications badly interfering with each other, as we've seen before. If you have a mice and elephant, you don't want them to be in the same channel, perhaps, right? Because the mice get destroyed by the elephants, assuming you don't make the memory scheduler smart. Think of it that way, right? If you keep the memory scheduler simple, you want to separate mice and elephants from each other because they badly interfere with each other. Similarly, if an application has lower overflow locality and another one has high overflow locality, the high overflow locality application denies service to the other application, as we've seen in the past. So we want to separate them to different channels. So these are very simple intuitive principles, right, based on what we've discussed so far. But we're applying them to partitioning right now. Okay, we already discussed this. High memory intensity application interfering with low memory intensity application. So let's take a look at a pictorial view of conventional page mapping. If you have this red versus blue applications, and they're both mapped to different channels, they interfere with each other. And this poor single request from the low intensity blue application gets delayed significantly, as you can see in this picture. And this picture is cooked up, as you can see, to maximize the impact. But this happens. This sort of thing can happen. As you can see over here, this blue application finishes after 4 time units, and the red application finishes after 5 time units. If you partition the channels in this nice scenario, you get rid of that huge delay against the blue application, as you can see. Now it finishes after 1 request. And you don't impact the performance of the red application. This is actually one of the best cases for channel partitioning. Right? Actually, you improve the performance of the red application in this case, right? For these requests. You save cycles on both applications. So that's one nice thing about channel partitioning. But it doesn't always work this nicely, clearly. So basically, the first key principle to take into account, but not to enforce in a hard way, is to map data of low and high memory intensity applications to different channels. The second one is separate applications by row buffer locality, and you're already familiar with this one also, basically conventional page mapping. These are, now we're looking at 2 applications that are similarly, not exactly similar in memory intensity, but not as bad in terms of memory intensity difference. But R0 these are row numbers over here. And with conventional page mapping and FR-FCFS scheduling, this is what you get basically. The blue application gets delayed significantly because it doesn't have good row buffer locality, and this one has good row buffer locality. And you can imagine having 128 requests like we've seen earlier. Okay, now if you partition these channels, you can improve the performance of the blue application significantly without impacting the performance of the red application, as you can see. Because red application, again, it was prioritized before, now it has a channel to itself, it's prioritized the same way. It's not getting delayed, but it's not improving in terms of performance also. Here, you're improving performance significantly by eliminating the interference from the application that has high row buffer locality. So hopefully it makes sense. Okay, that's the idea. Map data of low and high row buffer locality applications to different channels. Now the question is how you do it. Right. So this is a sophisticated hardware-software cooperative mechanism. It's mostly software, actually. Hardware essentially profiles the applications, and the software classifies the application into groups, partitions channels between application groups, and assigns a preferred channel to application. It's a preferred channel. It's a prioritization mechanism again. If you don't get a page from that channel, go to some other channel. And it allocates application pages to the preferred channel. Basically, it's hardware-software cooperative because all of this is done in that's done in hardware and this is done in software. In fact, you do better if you change your demand paging mechanisms to take into account this channel partitioning, because when you want to allocate a new page and you run out of your memory, now you have a question of which memory controller, which memory channel should you kick out the page from, right? If you have information about what applications or that you're doing channel partitioning, you could do more application-aware page replacement policies. Now, this paper doesn't go into that much depth in terms of page replacement, but I think that's really important. You really need to design across the stack, hardware, software together. So if you want to get the best performance out of this sort of partitioning mechanism. Okay, so let's take a look at. I don't know if I have all the slides over here, but okay, I don't have all the slides. I'm not going to go into detail basically of this one. But basically, it's also interval based. It again assumes that applications have steady behavior. You profile the application in this interval. At the end, you classify applications into groups, and then you partition channels between groups and assign preferred channels. And the next interval, you enforce channel preference. So how do you do that? Basically, you have a memory allocation request, right? That's when you really allocate a particular page in a particular memory channel to that application. And you have the channel preference of the application because you've done all of this. You basically said this application group should go into these channels, and this application group should go into these channels. There's some clustering that was done by the software again. And here, you basically need to decide which channel you allocate from. Now, the problem happens if that channel is essentially full, right? If you have some channels that are preferred channels, and that and the memory in that channel is full. What do you do? What do you kick out? That's what I was mentioning when I said if you actually change your page replacement policy to be aware of this, you can do much better. Does that make sense? Okay. Okay. We can go into a lot more detail on this one, but I prefer to give you breadth in the remaining time. So there are interesting things here, and I mentioned some of them, but this is an important one. And we had to handle this one actually, because otherwise you lose a lot of performance. So there are some applications that have low memory intensity, and they rarely access memory. Now these applications are actually good to prioritize in the memory schedule, right? But if you dedicate channels to them, you basically waste a lot of bandwidth. You have 4 channels, let's say, in a system, and you figure out that these applications are very not so memory intensive. And if you isolate them from other applications, you reduce interference. But if you dedicate channels to those applications, now you have a huge load imbalance in terms of memory bandwidth utilization across different channels. So it turns out it's really not a good idea to dedicate channels to these applications. So basically these applications actually have the most potential to keep their cores busy based on what you discussed so far in this lecture. We would really like to prioritize them. So here, and also the other realization that we also know is that they interfere minimally with other applications. These are really small mice. Prioritizing these small mice doesn't hurt other applications. Of course, there's always an end-to-end analogy, right? If you have a huge elephant, if you have a billion mice, prioritizing a billion mice over the elephant may be bad for the elephant. So you don't want to prioritize a billion mice. But we're not talking about a billion mice over here. We're talking about a handful of applications that are not generating a lot of requests. So once you have these observations, then I think the solution is relatively simple. You really don't want to do channel partitioning across all applications. So partitioning is a bad solution for cases where you clearly lose bandwidth. Basically, the idea in the paper is to integrate memory partitioning and scheduling. We set out by saying we don't want to actually change the memory scheduling. It's always good to go into extremes in research sometimes. You have the extreme idea, because if you push that extreme, you may enable something very different. And when we first set out to do this research, we said, okay, there's a lot of work on memory scheduling, very interesting, but it's getting complicated. So why don't we solve the problem in some other way and not complicate the memory scheduler? But then it turns out it's a better idea to complicate the memory scheduler slightly, because some applications really do not do well with memory channel partition, or the system doesn't do well if you actually use memory channel partitioning for all applications. So basically the idea is very simple now. You always prioritize very low memory intensity applications in the memory scheduler. You somehow identify them, and you can basically mark them with a single bit. So this is very simple. And you use memory channel partitioning to mitigate the interference between other applications. So it's a combined solution. Of course, you can now ask the question, what happens if an application changes behavior? And that's very not so, that's the Achilles heel for these data partitioning mechanisms. When you partition the data, you're assuming an application has some sort of behavior. If an application changes the behavior completely, for example, it becomes, for example, it used to be very highly memory intensive, it becomes very low memory intensive. It's changed behavior very quickly, but you have already assigned channels to this application, and you're not going to revisit those decisions for a while, because you already allocated the memory for this application. So what do? So these data partitioning mechanisms are usually not very adaptive because of this reason, because you need to move a lot of data. And that's where scheduling is very nice, because in scheduling you don't need to move data, right? You're basically directing which requests get prioritized over others. So these have fundamentally different properties, and unfortunately this is not a very nice, unless you have a mechanism to move data between different channels in a very fast way, which is yet to be invented. This Achilles heel for data partitioning mechanisms is going to remain, I think. Okay, but the good news is hardware cost, basically. Here you have only profiling counters in hardware that look at misses per kilo instruction and robobuffer hits. No modifications to memory scheduling logic if you use just memory channel partitioning, and actually storage cost is very simple. And actually, the hardware logic is very, very simple here. Most of the work is done by the software. And so in software you can do a lot more, of course. And if you use integrated memory partitioning and scheduling, you have a single bit per request in this case, and the scheduler prioritizes based on this single bit. But this is also very simple. I guess this could be a good assignment also, except now you'll have to deal with a lot of software algorithms to do the partitioning. Although you're already dealing with a lot of software algorithms. A lot of computer architects, good computer architects, are actually very good software designers. You may figure out that by working on simulators, for example. If you really want to make a lot of progress in big ideas, you really want to be a great software designer so that you can get that portion out of the way, so that you can evaluate your ideas. So what we do in hardware, in computer architecture especially, is really software in the end, right? You're really figuring out, using software, what is the next big thing to implement? What is the next big idea to implement in your system? Okay, so let's take a look at the results of this one. The results are in the end quite good, but again, these are also workload dependent, by the way. You can see that, what is this? This is memory channel partitioning. Purely memory channel partitioning without changing the memory scheduler, you get better performance across many workloads over here. If you do memory partitioning and scheduling at the same time, slight changes to the scheduling logic such that low memory intensity applications are prioritized, you get even better performance. And if you compare to TCM, which was the state of the art at that time, you can see that TCM makes a lot of changes to the scheduler. Memory channel partitioning doesn't make a lot of changes to the scheduler, but memory channel partitioning provides slightly better performance. Yes, it's not very high, but this comes at a very low complexity. And if you actually do slight changes to the memory scheduler, you do slightly better. And this is average across many workloads, as you can see. And again, take this with a grain of salt. All of these results will be workload dependent. And the paper has a lot of analysis in terms of different workload categories. Okay, I had to take this picture last night from the Zürich airport. Now you can see. So this is a real example of memory channel partitioning. There's a train over here. And this is the partition, basically. This is one channel that brings people. There's another channel, and I'm clearly here, as you can see. And this channel is heavily loaded. Although it's not the worst case, I've seen it much worse. And this channel is, actually there's no one there as far as I can tell. You can see that this provides isolation, but in cases where this is full, this basically have a huge imbalance in terms of utilization. And I've seen cases where this is completely full and people did not fit into this channel. As a result, they had to wait for the next one. Makes sense, right? It's very simple. It's very intuitive again. And people try to achieve similar things probably over here, right? They want to reduce interference over here. They want to balance load coming from different parts of the airport. But it's not easy. Okay. Oh well, I went back because I had to show you this picture again. Okay, so essentially you would really like to combine the interference control techniques and that leads to much better interference mitigation than a single technique can alone achieve. Of course, the key challenge is deciding what technique to apply when, partitioning work appropriately between the hardware and the software, and I don't think there is a good solution to figuring out exactly what technique to use when. So this is still an area of research. So let's talk about MCP and IMPS in terms of its pros and cons, and then we'll talk about the fair and superior source throttling, and then we'll probably be done with this. Although I'm open to your ideas. Basically, I've already said this. This is a dumb resources approach, and ideally, it keeps the memory scheduling hardware simple. It combines multiple interference reduction techniques if you actually do integrated memory partitioning and scheduling. And it can also provide performance isolation across applications mapped to different channels. So this is nice, and this is slightly, this is different from scheduling, right? Because you have this new degree of freedom, you can isolate some applications from each other. And this doesn't exist in scheduling. And general idea of partitioning can be extended to smaller granularities in the memory hierarchy, banks, subarrays, and there are other works that have covered this. And there are actually a bunch of works in software that try to partition the banks that with even better results than what I've shown you over here. Of course, there are downsides, and I've already given you one of the major downsides, which is reacting is difficult if workload changes behavior after profiling. You cannot quickly adapt. With scheduling, you can quickly adapt. Right? With memory channel partitioning, you have to move data. And data movement is costly and slow. And yeah, this is maybe related, but overhead of moving pages between channels restricts benefits. Okay, maybe you can read this paper for more. Any questions? Or any better ways of doing channel partitioning or partitioning? Not yet. Maybe after your assignment. Because your assignment is actually very amenable to the channel partitioning. You have a question, yes? To move the workload to a different channel, you mean?
Yeah, if it is both fluid intensive.
Yeah. Yeah, I think I agree. I think if you add more information, depending on how you design your mechanism, software profiling can be useful for sure. In this case, we added hardware profiling counters because those counters, like MPKI, and also actually more like row buffer hit rate, didn't exist, and we wanted that information for all of the applications. But certainly, you can imagine doing some of the profiling in software also, as long as you can do it in low overhead. Yeah. That's true. The downside is software profiling is often slow if you don't have some dedicated hardware for it. If you already have the dedicated counters, you can expose them to software, and that's relatively easy. But if you don't have the dedicated counters, it becomes slow. So you don't want to count, for example, every branch in software, because that introduces additional bookkeeping overhead, right? Any other questions? Okay. So in the remaining time, let me cover source throttling. Let me see if we can get to the last one. But the last one is very intuitive also. So this one I like a lot. This is really basically managing the interference across outside the system, essentially, outside the shared resources. Of course, it turns out the devil's in the details. If you want to manage interference outside the shared resource, you need to collect a lot of bookkeeping information inside the shared resources. And I'm going to cover basically this one. Essentially, we have many shared resources, and threads interfere with each other. Now you could implement smart mechanisms in each of these shared resources. Our motivation was actually slightly different. Basically, you could implement a smart cache, smart memory controller, smart interconnect, whatever you want to make it smart over here so that you get better quality of service. And you can put them together, but once you put them together, they may contradict each other. This is something that we did not discuss. Smart resources has this problem. You may have quality of service mechanisms in different parts, and if you put them together, they may actually contradict each other. And explicitly coordinating them can solve the problem. For example, your cache can prioritize an application, and that leads to some other application to become very memory intensive in the memory scheduler. And your memory scheduler may not prioritize that application. So overall, you may actually get very bad performance for some applications in the system, because you don't have the full picture in each resource. You're just looking at the behavior of that application in a particular resource. But if you can explicitly coordinate these resources to try to make up for that lack of coordination, but this requires complex implementation also. It's not so easy. Then the key question is, how do we enable fair sharing of the entire memory system by controlling interference in a coordinated manner? And this paper proposed a solution. It's really a substrate for fairness in the end. And the idea is source throttling. And I've already given you the idea basically. You control the injection of requests into the shared resources from the sources. Basically, you manage the interference at the cores or sources or agents, not at the shared resources. And this paper proposed a particular mechanism. It dynamically estimates unfairness in the memory system. So there still needs to be something done, as you can see. How do you figure out? The key question is basically, how do you figure out whether there's some unfairness, and how do you control that unfairness? It feeds back this information to a controller, which could be implemented in software or hardware again. And the controller throttles memory access rates of the cores accordingly. Basically, it decides which core to throttle and by how much to throttle. And it decides this based on a performance target. So if you're optimizing for throughput, the cores to throttle may be different, right? If you're optimizing for fairness, the cores to throttle may be different. If you're optimizing for a particular thread's performance, you really care about not throttling that thread probably, but throttling the threads that are badly interfering with that particular thread. Right? That's the idea over here. So it's really a substrate in the end. You have some substrate to figure out what's going on in the shared resources, estimating unfairness, for example. But you can estimate other things also, estimate all of the slowdowns, which is required for estimating unfairness. And you have some substrates to actually control the memory access rates outside the shared resources. For example, if you figure out that unfairness is greater than some system software specified target, then you can throttle down the core that's causing the unfairness, and you can throttle up the core that was unfairly treated. Again, this requires you to know which core is causing unfairness and which core is unfairly treated. That's why it requires some plumbing in the shared resource also. It's not as simple as, okay, I look at what's happening outside, and then I'm going to control. You cannot do that because you really need to know what's happening inside. Actually, you could do it completely outside, but at very high overheads. So you could, for example, track the progress of every single core somehow in system software, and you could compute the slowdown somehow, which is not easy if you don't have hardware support. And you could try to guess which core is interfering with each other, but it's not very easy. You have to run a lot of overhead. That's why I think it's doing it in the resources with some hardware support is a good idea. So let's take a look at this. This has two components. It's also interval based. You need to do some runtime unfairness evaluation in hardware, which dynamically estimates the unfairness, application slowdowns in the memory. It's very similar to slow time fair memory scheduling. You can assume it that way. There are some changes, but you can assume the basic idea is very similar. And you can estimate which application is slowing down with which other. So essentially, you can keep a matrix in the shared resources. You have the application that's causing interference, and you have the application that's receiving the interference. And you can quickly see, by doing very fine-grained cycle accounting, you can quickly see which application is delaying which other application. Right? Every time an application's request is scheduled, whenever some other application's request is ready, you increment the counter of interference between these pair of applications. It's relatively easy to do. You can guess this. But also, of course, you need to compute that matrix now. But you can do it. It's doable. And once you have that information, you can estimate the slowdowns with similar mechanisms to STFM. Again, it has all the downsides of STFM in terms of slowdown estimation accuracy. It's not very accurate. But you can also use other models that are developed later that can do better slowdown estimations. Right? So the key is estimating the slowdowns and unfairness. The next thing is dynamic request throttling. You could do this in hardware and software. For example, you could actually reduce the clock frequency of the core. That's one way of doing request throttling. Right? If you reduce the clock frequency of a core that's executing an application, it's not going to execute the application fast. It's not going to generate memory requests fast. But this is probably not a good idea because clock frequency affects not just memory request rate, it also affects how much computation you're getting done for the application. Right? So you need to do something else if you want to just affect the memory request rates. So basically, dynamic request throttling adjusts how aggressively each core makes requests to the shared resources and throttles down the request rates of cores that are causing unfairness. And the way that it's done in this work is you can limit the number of miss buffers. Basically, how many misses can you have outstanding to the memory system? As opposed to, let's say, 128, which is a lot, you can have only one. That, by nature, limits how many requests that you've injected into the memory system clearly. Right? On top of this, you can use other mechanisms. You can say you can only inject a request every 10,000 cycles. Okay? That's an injection rate metric. This is, you limit the space. Here, you limit the time. Right? And these are two different approaches, time and space. And we do both. And this actually turns out to be actually, in the end, this is a very complex mechanism. Complexity is basically keeping track of all of this and deciding what thresholds to use. In the end, internet congestion control is also a complex mechanism, I think. But okay, let's take a look at this. So basically, you have interval-based operation. In one interval, you evaluate the unfairness, you estimate the slowdowns, and you basically figure out the application that has the highest slowdown. Let's call it the app slowest. You figure out the application that's causing the most interference for app slowest. Let's call it app interfering. And I'm describing you one possible algorithm on this framework. And you basically send this unfairness estimate, app slowest and app interfering, to a dynamic request throttling engine. And the job of the dynamic request throttling engine is to check if the unfairness estimate is greater than some target, or if some condition is satisfied. And if it's not satisfied, it basically throttles down the application interfering and throttles by limiting its injection rate and parallelism. And it throttles up app slowest by increasing its injection rate and parallelism. Clearly, and you can employ different algorithms to throttle up and throttle down. You can do hill climbing, for example, to find a good spot. None of those are great, in my opinion. Whenever you have this sort of throttling mechanism, you're really at the mercy of all of those heuristics and thresholding. And it becomes not so easy to figure out what are your steps, what are your thresholds. Even though it's a good idea, I think, the devil is in the details over here that makes it relatively complex. So let's take a look at this dynamic request throttling engine. Basically, you want to adjust how aggressively each core makes requests to the shared memory system. And one thing is having a quota for each core and controlling the number of concurrent requests accessing shared resource from each core. And the other is request injection frequency, as we discussed. Right? How often memory requests are issued will last all cache from the miss buffers. And this hopefully gives you an example of the complexity of the mechanism. Right? Basically, somebody needs to come up with these throttling levels assigned to each core based on MSHR quota and request injection rate. So this is the full throttling, full quota. You're not throttled at all. So every cycle you can inject. This is your throttle the most. Your throttling level is 2%. You have an MSHR quota of 2, and you can inject once every 50 cycles. But this gives you the design complexity now of all throttling mechanisms. All throttling mechanisms that I know of have this sort of throttling. Blacklisting is also a throttling mechanism if you think about it, right? It's incorporating throttling into the scheduling. You're blacklisting an application, which means that you're deprioritizing it for a while. Here, you're really truly throttling. You're not really deprioritizing. You're basically not injecting into the system. And you need to have a threshold, basically. And you need to determine your level. That's true for blacklisting also. And here, the problem is more complicated. So you can always say, why 50 cycles? Why not 500 cycles, right? So whenever you're designing a throttling mechanism, you will run into these issues. No question about that. If you don't, let me know. because that's probably a very novel throttling mechanism. Okay, so there's system software support also. Basically, you can configure different parents objectives. For example, you can keep the maximum slowdown in check. For example, you can try to keep estimated max slowdown below a target max slowdown, or you could keep the slowdown of particular application in check to achieve a particular performance target. Basically, it's very configurable, and you're doing this with throttling. And there's support for thread priorities. Basically, you can scale the estimated slowdown with some weight. So essentially, let me give you the takeaway results. It turns out, in these workloads, source throttling alone provides better performance than a combination of smart memory scheduling and fair caching, because in some cases, these memory scheduling and fair caching algorithms are not really going well with each other. They contradict each other. You could argue that they're not the mechanisms that are designed together, but that also gives you the complexity of smart resources. But it also turns out that neither source throttling alone nor smart resource alone provides the best performance. Basically, sometimes source throttling is good, sometimes combining a pair caching and smart memory scheduling mechanism is good. You really want to get the best of both worlds. In the end, I think you really need to combine these mechanisms to get the best of both worlds. Combined approaches are essentially more powerful. You really want to do this: source throttling and resource-based interference control. I think before we part, let's talk about the advantages and disadvantages of source throttling very quickly. Essentially, throttling itself is easy to implement. No need to change the memory scheduling algorithm. It could be a general way of handling shared resource contention, and it can reduce overall contention and load in the memory system. This is also very important, actually. This doesn't happen. This is an advantage of throttling that doesn't exist in scheduling or data mapping. By throttling, you're really reducing the overall load. And if you remember this curve very quickly, we're going to see this load latency curve again. But basically, this is your load on the system. How many requests are there? And this is the latency. And all systems have this sort of curve. At some point, they saturate the throughput, which means that latencies shoot up. And if you're operating over here, it's very hard to get this system performance higher or handle some quality of service. Throttling actually takes you down somewhere here in this curve. Basically, it reduces your load in the memory system. And that could actually be good for overall performance in the end. And clearly, scheduling cannot do this. And clearly, data mapping cannot do this also, right? So it's very powerful in that sense. And you really want to do this sometimes. You don't want to overload your system. But of course, this has disadvantages. One is requires slowdown estimation. It's difficult to estimate. We know that. Threshold can become difficult to optimize. And this is actually one of the worst parts of this sort of mechanisms. How do you decide the thresholds, throttling levels, etc. And also, if you don't do it well, you run into the other problem, which is you lose throughput now, right? Because if you throttle the core too much for too long, that core is not really injecting any requests. It's basically stalling, right? And that's very dangerous because that reduces your system throughput a lot. So you need to be very careful in these thresholds in the end. That's why this is very difficult to, even though this says it's an easy to implement mechanism, it's conceptually easy to implement, but practically it's very difficult to get it completely right. You may get a working solution, but it may not be the best solution out there, or it may not even be close to the best solution. Okay, this doesn't mean that there's no hope, but this is another example where humans are actually not very good, I think, in terms of thinking about these throttling levels, thresholds, etc. Okay, I think this is, well, basically, there are a lot of works related to this, which I'm not going to talk about, but basically throttling is a very general approach on all resources, in terms of network resources also, but we're not going to talk about that. Okay, tomorrow we'll pick up with this one, finish up very quickly, and then we'll cover other topics.